All right, we're going to go ahead and get started here this morning. Today we are doing our microirrigation TDP. We're going to start out with some brief overview of microirrigation as a whole, and then we'll go into a design example to show our spreadsheets that we use to complete the design. Just a forewarning, the time today is probably going to look more like 2.5 hours rather than two. So if you need to leave early, this is going to be posted on DSWC's YouTube page for future reference. So you can step out whenever you need and you'll be able to reference this again in the future. That being said, after our first round of presentations, we're going to do a brief break where we will answer some questions. We'll also be trying to answer questions in the chat as they come in. So yeah. All right. I'm Alyssa Bowles and Logan Beely, NRCS Area 5 engineer, is also going to be helping with the presentations today.
Morning, everyone. Hello, everyone. Welcome to the 2026 TDP on microirrigation. We're going to cover a lot of microirrigation systems, and then at the end go through some of the design process and the new design tool for microirrigation in Ohio. I'm Logan Beely, the USDA NRCS engineer down in Chillicothe in Area 5, and helping along with this presentation will be Alyssa Bowles, the ODA engineer down in Area 5 in Chillicothe as well. Giving a quick look into what today is going to look like with the microirrigation TDP. First, we're going to start out talking about irrigation in general, a lot of microirrigation fundamentals and terminology. That'll transition into the water sources, and then some example system layouts and example applications of where micro may be used. Next, we'll get into a quick discussion on kind of the standards and associated practices we're probably going to see in the field when we're designing a microirrigation system, and then some of the drafting tools or details available to present these in engineering drawings. And then lastly, we're going to go through kind of the tools and resources available, and Alyssa will walk through a design example using the NRCS micro design tool. So today we'll start out by just discussing some of the fundamentals, the basics, the terminology surrounding irrigation in general, and then we'll transition into what are those fundamental components of microirrigation as we work towards a micro design. Starting out, we really should define what is irrigation. Loosely, irrigation can be defined as bringing additional water to a plant, so supplementing a plant that either is not receiving enough water, needs additional water to grow properly or to produce more crop, and providing and delivering that water to that root zone of the plants. So when you look through history, really irrigation dates way back, and there's evidence of irrigation in the Middle East in the Jordan River Valley all the way back to 6000 BC, where these ceramic pots were buried alongside plants and manually filled with water to then disperse additional water into the root zone and irrigate those crops. As with other industries and with agriculture, irrigation developed throughout time as well. And looking into some more modern irrigation history, really before the 1930s, most land was irrigated with flood irrigation or type of surface irrigation where water is gravity flown across a field to irrigate different rows. In the 1930s, the impact sprinkler, shown in the bottom right picture, was developed, and that really started altering a lot of the aspects of how irrigation was designed in crop fields. And some really good examples of where modern irrigation technology has really shaped the world that we live in comes into play in the settlement of the Great Salt Lake Basin in Utah, where previously there was an area, where crops and settlement was incapable, but due to irrigation, that land has been transformed. As irrigation technology continued to develop, we moved into the next big development in the 1960s when Chapin Watermatics developed the first drip tape hose named the Dew hose. And this is going to transition us into what we're discussing today with microirrigation. So then in 1964, the Netafim company was formed and developed really the first practical drip emitter that was started to be used in larger scale operations. So now that we have a little background of what generally irrigation is and the history of where it kind of started, why are we irrigating different crops in different pieces of land? So when you look into arid regions where there isn't enough water to sustain crop growth, that irrigation may provide most of what the crop needs to grow. So in these situations, irrigation can be applying up to 30 inches of water or more per year per growing season. Where in humid regions, where you're looking more into how irrigation is used throughout Ohio, it's a supplemental to the rainfall, so you're able to withstand drought or dry periods and ensure that the crop being planted is productive and producing the greatest yield possible on the land. So typically, when you're thinking of that supplemental use, you're applying 4 to 12 inches during the growing season of water. Um, so then the questions become, this is why we're irrigating, but what method are we going to use? What time periods? When are we going to irrigate? And how much water are we going to add to those fields when we irrigate? So giving a more visual representation on why we may irrigate. So first we'll start with the field on the left, where we have crops that are growing in a field that is only supplied with rainwater. So that rainwater will fall down. Some of that rainwater may run off the surface. Some of that water will infiltrate into the soil. Of that water that infiltrates into the soil, some of it may percolate deep below the root zone and be lost to deep percolation in the soil. But a good portion of that water is going to undergo evapotranspiration. So that's either water that's on the surface or in the soil that's evaporating, or as the plant is transpiring, that water is being released back into the atmosphere. Now, on the right, we may have an irrigated field, and it's going to undergo the same inputs and outputs of water, but as we may lose more water than what we're gaining, or we go through a dry spell where we're not having enough rainfall to keep up with the outputs and the losses of evapotranspiration, we may supplement that water with irrigation to provide the water that the crop needs. So you can kind of think of it as when you're planting crops in a rain-fed system, you're kind of rolling the dice. You're subject to the weather and to any drought conditions that may be imposed. Whereas an irrigated field is going to have, be more resistant in a drought period. It's likely going to increase the yield of the crop as it's always being provided the amount of water that it needs, and it's going to stabilize that yield from year to year. So as we kind of discussed in that last slide, right, there's inputs and outputs into this soil water plant system that's at this crop field. So where water is coming into the system, the inflows are through precipitation, right, rainfall events. We may be supplementing with irrigation, adding water during those periods where the precipitation isn't keeping up with the needs of the crop. Or there also may be some capillary effects where there's some upward flow, flowing water into the root zone. Now, the water is also flowing out of the system, primarily through evapotranspiration, where water is evaporating or being transpired by the plants. During heavy rainfall events, some of that precipitation may turn into runoff and run off the landscape, or some of that water that's absorbed into the soil could be percolate deep below the root zone and be lost to deep percolation. So those changes in storage of water that we have in this soil kind of box shown on the right is really that soil water in the root zone, and that's what the plant needs to have sustained during the growing season. And we're going to discuss some of this further on the next slides. So when we're thinking about the water stored in the soil in that system, there's really three levels that are pretty important to the irrigation system that we may be designing. So the first, starting at the top, is the saturated condition, right? So this is where there's so much water that all the space between these soil particles are filled with water. There's excess water. It can't absorb anymore. That sponge is completely full, and we keep adding water to it. We may have some ponding. We may have runoff. Now, a few days later, when that field is, able to drain some, um, after the gravity has dissipated all that excess water that couldn't be absorbed, but that maximum amount of water that that field can have in the sponge can be absorbed is that field capacity. And then really at the other end of the spectrum, when we go through a drier period and we haven't had any addition of water from rainfall or irrigation, the plants growing there will extract as much water as they can. There may still be some water in the soil particles, but it's beyond the point where The forces that the plant are able to exert can't extract it, and at that moisture level, the plant will begin to wilt, and that wilts beyond recovery and impacts the growth of the plant. So really, in any irrigation system we're designing, we want to avoid reaching the wilting point of the soil. An important design criteria in an irrigation system that really stems from those conditions of the field between the field capacity where it's completely saturated and full of water and the wilting point where the plants begin to damage is known as the available water holding capacity. So you can think of this as what range do I have to work with where the soil is full of water before I get to the point at the bottom where the plants are going to be damaged because we're at the wilting point and there's no more water available. So you're right having that sponge 100% to 50% full to 0% at the wilting point. Now, just to clarify a little bit further, right, gravitational water is some of that water that's drained by gravity. So gravitational force is greater than what the forces between the soil particles keeping the water in, and that's during that saturation period where some of that excess water that can no longer be absorbed is going to be lost and run off or be left to pond until percolated later on. So the field has a total available water holding capacity. And right, that's from the extreme of the field capacity where it's full of water all the way down to that wilting point where the plants are being damaged. But when we're designing the irrigation system, really we'll want to design and have an understanding of what is our management allowable depletion. And that is the trigger and the point at which when the water in the soil reaches our MAD, we want to initiate irrigation. And typically that's around 50% of the total water available in the field. So, we have some buffer room there before we get to the wilting point because you really want to avoid that. But right, we're not always irrigating right after we're below the field capacity. An example of what that management allowable depletion kind of looks like. So right, that top curve where we have what the field capacity is, the maximum amount of water that's stored in that field based on some of the different soil textures. We have a pretty high frequency of where we're going to be supplementing irrigation, where that water in the soil is going to fluctuate in. But as we creep down and we get to that, MAD, at that we hit that point, we might want to kick on our irrigation. But you can see that's always going to be above that wilting point where there's unavailable water for the crops being grown. Transitioning a bit into some terminology about irrigation, and that'll come into play later in our microirrigation discussion, is emission uniformity, or EU. So as you can see in the two pictures, top and bottom, we'll start with the top. We have a crop field, we have a darker soil that's representing a irrigated or moist soil, and then in the lighter brown, we see that that's going to be the dry soil. So in this situation, that root zone of where those crops need water, if we have a poor EU or a low emissions uniformity, right, our irrigation isn't very uniform across the field. So there's going to be instances where the crops are not obtaining enough water, and you can see those crops are a little shorter, they're not growing as much, or there may be instances where we're over irrigating, we're providing too much water to certain plants. And right, that's effectively overusing the water resource that we have available. Now, if we have a improved emissions uniformity, and it's never going to be perfect, right? We're going to have a little bit of fluctuation based on the soil, the topography, what irrigation system we're using. But we can get a lot closer to applying the same amount of water to every plant at that root zone at the amount that we need at the right time. Now that we've discussed some of the terminology and a lot of that background information of why we may be irrigating and what kind of irrigation is, how are we going to irrigate? So really there's four main ways that irrigation is performed across agriculture. So starting in the top left, we have surface irrigation, and this is gravity flow. That usually has pretty low to medium efficiency. You're not going to have great emission uniformity with that system. On the top right, we may have sub-irrigation where we have a drainage water control system. We're controlling that water table in that field and lowering and raising it accordingly to get that water up into the root zone. In the bottom left, we may have a sprinkler system such as a pivot that is going to irrigate the field with sprinklers, and we'll go through that in further detail here in the next couple slides. Or kind of the discussion today, the focus today is really those micro systems, and those can be called drip or trickle systems as well. Starting with surface irrigation, there's a couple really main common types. On the left, you may have furrow irrigation with siphon tubes where you have a main channel, irrigation channel that was providing water, and water is being siphoned up and over a furrow into the different furrow rows to irrigate the field. We may have a basin system where, again, a field channel is supplying water into more of a flood basin to irrigate that field, or on the right, something as simple as a gated pipe, and that pipe is releasing water directly onto the surface to then gravity flow across the field. Surface irrigation comes with its own set of challenges. So as you can see in both the diagram on the left and the actual field pictures on the right, typically surface irrigation struggles with low uniformity and low efficiency of that water being used and distributed throughout the field. For example, these furrow irrigation rows may have some soil that was shifted around during planting or during spraying or during some wind blowing it around, causing the water paths to not flow quite evenly or be a little different slope, and that's going to impact how that water is distributed throughout that field. And as it's distributed less uniformly, you may have to over irrigate in certain situations to provide enough water to all of the crops, and that's going to reduce the efficiency of the water being used in that field. I think many times when we're thinking of irrigation in the agricultural setting, we're thinking of sprinkler irrigation. When you look out west, or in my case, in Area 5, look along the Scioto River Valley, we see a lot of center pivots, for example. And these are pumping water from a well, pivoting these booms around a center point in a circular path with these drop-down sprayers to distribute that water to all the crops in that field. Very similarly, a boom system is going to have two booms, but have a linear path of travel with those drop-down sprayers to pump and disperse that water to the field. Some alternative types of sprinkler irrigation that you may see are wheel lines, and they're going to travel similarly to a boom in a linear fashion and spray as that wheel line moves across the field. Or there may be a traveling gun where there's a reel, and that gun will go across the field and then retract and then maybe set on a different path to irrigate. All of these sprinkler irrigation systems have different types of sprays or bubblers, and all of these nozzles, are what is directly applying that water to all of the individual plants. Last but not least, that brings us to the topic of the day, microirrigation. And microirrigation is really a pretty broad classification of irrigation. And you can think of it as pretty simply the application of water right at or on top of or right beneath the soil surface. And all these different types of microirrigation that we're going to discuss in the coming slides all have these same things in common, where it's frequent irrigation at really defined areas at a low volume of water, really specific to where it's needed to be applied, and they typically operate at a low pressure. So we're going to talk about some of the different devices that are used in microirrigation, and microirrigation can include emitter systems, drip tape systems, micro spray systems, or sprinklers, and we're going to provide a lot of examples of what those look like. Microirrigation can occur really on three levels you can think of. It can occur at the surface, right? So we have our microirrigation lines depositing water or distributing water right at the soil surface. It can be subsurface lines where those lateral lines are running just below and more permanently installed into the root zone, or it can be a micro spray system where that small area is being irrigated with that micro sprayer on the surface of the soil. The next couple of slides are going to go through really an overview of microirrigation systems, and we're going to start talking about the different components that go into building that system. So we're going to have some schematics that show the layout of these systems and kind of diagrams to walk through them. So when we look at a microirrigation system, really they're all going to have some pretty common components, right? We're going to have kind of this control head area where we're going to have filtration, the ability to introduce chemicals for chemigation or fertigation. We're going to have, other filtration systems, flow control, flow meters, pressure control. From that control head, that's, tied into that farm water supply. We're going to have that main line where water is going to be distributed along the main line and piped where it needs to go. You may have a sub main, you have any control valves along that period. From that sub main, we're going to go into our manifold hose. So this manifold is then going to distribute to a full zone. This micro irrigation zone is then going to be made up of these lateral lines, and each of those lateral lines is going to have an emitter, and that is where at each emitter the water is going to be distributed to the irrigated area and to the plant. Then at the end of these zones, we're going to have flush lines to be able to flush out the system and clean any buildup. Again, just providing another example of kind of some schematics. We're going to have some of our water source supplies. So we may be pumping from a well or a pond, for example. We're going to go through any backflow prevention, flow meters to regulate our flow. At this stage, we may be introducing any chemicals for fumigation or fertigation, go through our filtration system. In this diagram, it may be a media filter, regulate our pressure. From there, distribute that water through a main and sub-main lines to our manifolds. Those manifolds then have laterals running across and emitters along those laterals. And then at the end, we're going to have flushing for maintenance of the system. Providing another schematic of what goes into a system. This one is really broken down to kind of the basics. We're going to have some water source. We're going to add some energy, through a pump usually of some sort. From there, you may introduce chemicals through fumigation, go through some filtration process. You're going to convey that water through your distribution pipes, your mains and sub-mains. You're going to have your main lines and your laterals and all your emitters where it's going to distribute that water and micro-irrigate the field and the crops in that soil. And then at the end, you're going to have some flush systems for maintaining your micro-irrigation system. So on all those micro irrigation diagrams, right, everything starts with our water source. And we're going to need to do that when we're going out on site to design an irrigation system. And when designing our micro system, we want to have a good understanding of what is the quantity of water we have available to irrigate with, and what is the quality of that water that we're going to irrigate with. The next few slides, we're going to cover some of the common water sources that we're going to see in micro irrigation systems used in Ohio. So the first is rural water or county water, municipal water systems. So these are going to be really good for those smaller operations. We're going to use these a lot in our high tunnel systems, and we're going to have some sort of pressurized line on the farmstead that we're going to tie into. It could be at a frost-free hydrant, and we're going to use that hydrant to supply our control head, for example, in a high tunnel system. Right, rural water is going to provide a really consistent water supply. We're going to have typically ample quantity of water available with the pressure in the line, and typically it's going to be a very consistent high quality water source. Now, some considerations that the producer may bring up and are part of the discussion in their water source is, right, as that operation grows in size, the water usage is going to grow, and therefore the operating cost of the rural water is going to grow as well. So while that may not be a resource concern situation that we are able to address from our fundings, it still should be something we should understand in that discussion with the producer. Secondly, wells are also a very common source of water for irrigation systems in Ohio, right? We're going to classify these into kind of two different categories, really. The typical small diameter well that we might see at a normal farmstead, right? A 6-inch or 8-inch well. We're going to see our well logs that are going to provide us some information on the depth of the well, if we're sizing a pump, and what capacity the well may have been tested to when it was drilled. So, right, current guidance in Ohio requires us to do a constant rate pumping test at around 1.5 times the needs rate that we're going to have for our irrigation system to ensure that the well is able to provide the water we need. When we get into larger, irrigation systems such as center pivots, or we're irrigating larger amounts of acreage, we may get into larger diameter wells, and then in that instance, we may want to rely on our full-fledged aquifer testing to ensure that we're able to provide adequate water for the system. Additionally, when we're looking to use wells in Ohio, one thing to consider is the quality of the water coming from that well. We may encounter wells that have very hard water where there's a high number of total dissolved solids, right? Those suspended solids may precipitate out throughout the microirrigation system, and this can lead to problems such as emitter plugging, like on the drip line in the bottom left. The last water source that we're commonly going to see in Ohio is pond or surface water. While there are benefits to utilizing pond and surface water, there's also a lot of considerations that need to be taken into place when utilizing this. So, right, first, a pond can be utilized for water recovery, right? Either we're having some sort of tailwater, some sort of drainage water that we're recovering from a system, and we're able to recycle that and then reuse it to irrigate the fields through a pumping plant. Some additional consideration is going to need to be taken into place for the quality of the water, right? If we're having a lot of nutrient-rich runoff entering that surface water, or what filtration we may need for algae. All those need to be taken into consideration in your microirrigation design. And then really lastly, right, what is the reliability of that water supply? And as we would go through times in the summer, maybe of dry periods or a drought period, when that irrigation system needs to be relied on, is that pond going to be able to sustain and deliver the capacity of water that's needed? As we get into planning and designing our microirrigation system, it's important to try to gather as much information as we can, especially about the water source on the site. So a really simple test that we can do to gather some information to help us in our design process is to just take the stopwatch on your phone, take a 5-gallon bucket, have a valve with a pressure gauge attached to it, and evaluate what's our relationship between our pressure on site and the flow rate available by the water source. So creating that relationship, we can make sure that the microirrigation system we design is able to be supplied by the water source on site. After the water supply, we get into the different components of a microirrigation system. So we're going to go through the next slides of different components and show example pictures of what those components may look like in the field. The first we're going to talk about is just controllers and timers, right? We need to have a way to control when our microirrigation system is on, when it is off, what field is it running to. These can vary in complexity from something as simple as a manual timer that we may twist on for a set irrigation time to a multi-zone controller with automatic valves that are going to open and close and control the water distribution to multiple fields and irrigation system, throughout a full, let's say, 20-hour irrigation period throughout the day. The controller for the microirrigation system is going to tell the system when it needs to turn on and off. And the ability to turn on and off is going to require the water in that system to be energized in some sort of way, right? So if we're running our system off of raw water, that water is already going to be pressurized in the system and supplied then to the microirrigation lines. If we're supplying water from a well or a pond, we're going to need some sort of intake pump to pressurize the water and deliver it throughout the system. So these could be things such as a submersible pump in a well. These could be things such as a vertical turbine pump in a shallow well, or a centrifugal pump may be used in a different application. From that pump, it's going to go to likely a pressure control switch of some sort to know when to cycle that pump on and off, and that pressure control switch is going to control the pressure in a pressure tank to reduce the number of times that pump's going to be cycling and still energize the system more consistently. Once we have that water in the system energized and pressurized, we need to have a way to be able to control that pressure, and that comes in play with a pressure regulator. So closer to the supply, we may have a regulator that's setting what that pressure is as the water is traveling through our main lines and distributing throughout the system, right? We want to be able to protect any of the components downstream from overpressurization. As we get into our manifold hose and tubing, right, as we discussed earlier, that microsystem operates at typically a pretty low pressure. So you're thinking using something like these inline pressure regulators set to 10 psi, 15, 20, as low as 8 psi. And those are then going to protect all the lateral lines downstream and evenly distribute the water per the microirrigation design. Alternatively, there also may be pressure relief valves throughout the system. These pressure relief valves prevent the system from experiencing overpressurization from a closed valve or a plug in the system that may damage some of the components. So rather that pressure building up, when it reaches a certain set point, this relief valve is going to release that pressure and protect those downstream components. Some microirrigation systems may utilize the processes of chemigation or fertigation to apply pesticides or fertilizer to the crop field by injecting it into the irrigation system. So as we're irrigating this field and applying water to the different crops, the suspended or dissolved chemicals will also be distributed throughout the field. Now there's going to be some different components that you're always going to see with a chemigation or fertigation system. You're going to have some sort of backflow prevention valve. These are to ensure that the chemicals being injected are not going to backflow through the system and contaminate the source water. We're going to have some sort of storage tank, such as a bulk tank or canisters. And then lastly, we're probably going to have some sort of injection pump, so we're able to monitor and regulate how much and what rate that chemical is being added to the irrigation system into the water flow. Along the lines of having a chemigation system, we're going to have some sort of backflow prevention installed, right? This could be something such as an air gap shown here on the left, where water is able to gravity flow into the remainder of the distribution system, but that water is not able to flow back up into the source, preventing any contamination. Commonly, we'll see something like this, a chemigation check valve where water is able to flow in one direction, in this case from the right to left, but the check valve then prevents any backflow after that chemical has been injected to the system. Another variation of a type of check valve is going to be an air vented gooseneck valve, shown here on the right. Filtration plays a critical role in any microirrigation system. We're going to see in future slides the emitters on many of these microsystems are rather small, and we need to prevent them from clogging to ensure that the microirrigation system is going to operate as designed. So some common filters that we're going to see on microirrigation systems are screen filters, right? These are mesh filters down to a certain size mesh. A lot of times these are going to be spec'd by the manufacturer of the emitter or drip tape of what size mesh needs to be installed. When a system that is more complex or larger, we may have sand or media filters, and these are going to be more capable of filtering out things such as algae. And when you're thinking of what a sand and media filter is, effectively this is just a super fancy pool filter that most of us may see on an above ground pool. Alternatively, there could be disc filters where stacked discs filter the water, or centrifugal filters shown here on the right. There are some additional appurtenances that we may see throughout our microirrigation system, or primarily towards the control head. One of these may be a flow meter. The flow meter can help diagnose if there's any problems with the expected flow of water going through the system. One thing that I always like to see is a pressure gauge, right? This is a pretty inexpensive way to monitor the system, make sure we're operating at the pressure we expect to, and ensures that that pressure regulator that we installed is doing its job. In more complex or systems that have a lot of different varying terrain, we may need to install air or vacuum relief valves to ensure that the pipeline doesn't vacuum lock and prevent water flowing. With all of these different pipes, we're going to have some valves. So different types of valves we may encounter from left to right are butterfly valves, gate valves, ball valves, or globe valves, all of which are designed to effectively shut or restrict the water flow into different parts of the system and isolate different lines if there's need for repairs or to redirect water to different locations. From the different appurtenances that we covered in the control head, we now have water that's energized to that set pressure, and the controller is determining when and where that water is being directed into the different microirrigation zones. We need a way to be able to convey that water from the source out into the fields and then distribute it to all of the different microirrigation zones. Typically in Ohio, this is going to be achieved using a buried pipe situation where we're burying that pipe and installing it below the frost line. In any equip contract, we're going to be utilizing and designing under Conservation Practice Standard 430 irrigation pipeline. Most commonly, We're going to see in the field polyethylene pipe used, such as this SIDR-PE pipe under ASTM D2239. We also may see situations where PVC pipe, such as Schedule 40 PVC, is utilized to distribute that water out into the field. With water being transported from the source to the field and the microirrigation zones with our main and sub-main pipes, we now get into the layout of what the actual microirrigation zone looks like. Each microirrigation zone is going to have a manifold pipe, such as a solid PE pipe here that is above ground or below ground in a more permanent buried situation, such as this subsurface microirrigation. A lot of times we'll commonly see lay flat manifold hoses used as well. These are very popular as when they're not filled with water or being operated at that low pressure, it's easier for equipment to drive over them without them cracking and being damaged. So on each manifold hose, right, we're going to have our bed arrangement, and these lateral lines are going to either stab into or have some sort of fixture to attach them to the manifold. From the manifold tubing, we're going to have lateral lines across that microirrigation zone to further distribute the water. So each lateral line is going to have some sort of connector to either stab in or fix it to that manifold hosing, and then the lateral lines are going to run across and in between the different crops. So from our manifold hose, right where all those connectors are stabbing in, we're then going to run our lateral lines across the microirrigation zone. Two common types of lateral lines that we're going to see, firstly, is a drip tape. This is going to be a thinner wall pipe, and it's going to have inline emitters likely already installed, and we'll discuss some more examples here in the next slide. Or a drip hose, which is more going to be a thicker wall where point source emitters are going to be installed. At this stage, we've taken water from our source through our control head. We start distributing it down our main and sub-main lines out into the field. We get to our microirrigation zone where we have a manifold tube. The water then travels down one of our lateral lines where we arrive at our microirrigation emitters. And these emitters spaced along that lateral line control the discharge of that line and how much water is being applied at each spot along that lateral. There are three main types and groups of microirrigation emitters. Firstly, there are point source emitters, and these discharge water at an individual spot in relatively wide spacing throughout beds, where we may have crops that are spaced further apart. Alternatively, we could have line source emitters such as drip tapes, and these are emitters that are typically formed within the tape itself, within that lateral line, and water is discharged from closely spaced perforations along that wall in the pipe. And then lastly, we could have micro sprays. These are small sprinklers or sprayers that provide a localized spray to a crop or plant along that lateral line. Showing some examples of point source emitters that we may see out in the field. As we stated, point source emitters are typically used for wider space plants, really good examples that they may be utilized or in fruit trees or in vineyards, right? We may have some punch-in emitters for lower flow rate applications that are punched into that more thicker wall drip hose that's run along as a lateral line. In larger flow rate applications, we may have items called basin bubblers, right? That lateral line is going to run down, and that basin bubbler is kind of going to fill that full basin of soil that's formed around that tree, that fruit tree, to irrigate that area. Moving on to line source emitters, this can commonly be referred to as drip tapes, right? These drip tapes are these thinner walled lateral lines that connect to our manifold hose. Along these drip tapes, we have molded or glued internal emitters that are set at equidistant intervals along that lateral. Our drip tapes can come in pretty common sizes we see are 5/8 inch and varying wall thicknesses. And then these emitters can be spaced anywhere from 8 to 24 inches along that lines. And then based on the set pressure of our design, they may have some different flow rates. So these emitter spacings should be selected to fit this plant spacing that we're irrigating in that bed or in that field. And flow rates along these lines are typically expressed in rates of gallons per minute per 100 foot of section of that lateral tape. Looking at the last type of microirrigation emitter that we might encounter, we're going to look at microsprays or microsprinklers. So you can think of these as devices that apply water to that local soil area with a small spray or mist or stream. Manufacturers are going to have different throw patterns such as mini sprays, micro sprays, micro jets, spinners, and really a lot of these designs have a large fluctuation in what the application rate is going to be based on the design's orifice size and the line pressure being designed with. So for example, we have spinner here shown at the right, some micro sprays overhead in a greenhouse situation, or some micro jets here on the bottom right. Typically, we're going to see these micro sprays or sprinklers on a lateral line with a small pigtail coming off to then have that sprinkler fixed on a stake. A lot of times we'll see these applications used in crops that are spaced further apart, such as fruit trees or in vineyards. A unique type of point source emitter that we may encounter or design with in situations where there's varying topography and we're struggling to get a good emission uniformity is a pressure compensating emitter. So what these do is they deliver a consistent emitter flow rate even when there's pressure changes along that lateral line. And these can be really beneficial in very long rows where at the end of the row water pressure may be decreased due to the friction experienced along that lateral line, or if we're having a lot of variations in terrain that are making that difficult to design. Now, one thing to consider though is when we're below the operating pressure that these are designed for, the pressure compensating emitters can actually have reduced performance compared to other emitters. Lastly, at the end of the lateral line, we need to have some sort of flushing valve to be able to maintain and clean the microirrigation system. There may be flushing valves that attach to the lateral line and then are able to be opened and closed accordingly, or it could be something as simple as a crimped tape end to prevent water from flowing through, and then that crimp is removed when we're going through a flushing cycle. Now we're going to look into some example system layouts and example applications of where these components may look like in a microirrigation system in the field. First, we'll look at where that microirrigation system is located at vertically within a bed. Microirrigation laterals could be suspended, such in a vineyard situation where there's posts and wires supporting the crops and vines that are growing on. That manifold tube could be suspended and strung along that with the emitters directed downwards to the different crop and soil locations. Most commonly in Ohio, we're probably going to see surface microirrigation, where that drip tape or drip line lateral is run on the surface, either along where the crops are planted or along that raised bed area. Alternatively, there could be subsurface microirrigation, that subsurface drip irrigation, where that irrigation lateral is more permanently installed under the soil surface. Next, taking a look at the XY direction, we want to understand how can our microirrigation emitters and drip tapes be located in each bed, right? We need to have a consideration of how many tapes per bed we're designing for, how many emitters we're designing for, what is that emitter spacing, right? We may have situations where we have travel or walkways between our beds, or we have a lateral line that has pigtails coming around with multiple, single or multiple emitters around a fruit tree. Alternatively, we could have situations where the bed is pretty narrow and we're only running one line of drip tape through that bed. Starting with some examples of smaller scale micro irrigation systems and layouts that we could see. These are going to be examples of smaller high tunnels or smaller beds or zones where we're irrigating crops that have a specific purpose. These smaller systems a lot of times are going to be supplied by either a well or a rural water system, or we'll be tying into some sort of frost-free hydrant. We may run some main lines out to these different zones that we have, and then we have our lateral lines to distribute our laterals down through the different beds or some pigtails around these trees to irrigate accordingly. A second example of a smaller scale microirrigation system and how we may lay out the different microirrigation zones and beds. We may have a system where there's small beds of edible flowers and herb gardens and two smaller high tunnels. Uh, in those systems, it may make more sense to place multiple hydrants and run manifold tubing directly off of that, and then our associated lateral lines for each zone. Looking at some common layouts that we may see in, for example, a 30 by 90 high tunnel, we may have that hydrant from our main line from the source placed in either the center or at the corner of the high tunnel, that manifold tubing running across the top of the high tunnel, and then our different beds and walkways running the length of the high tunnel with, in this case, 2 drip tapes running through each bed. Moving into some examples of larger scale micro irrigation systems, you want to think these are when we're irrigating a field or multiple field systems, and good examples of where these really come into play are orchards or vineyards as well. So in this case, we may have, a rural water tap here. At this place, we really don't need a lot of main line to deliver the water. So we're pretty much going to have just our manifold tubing for each zone. So zone 1 may be this north field, zone 2 may be this south field. Uh, that manifold tubing runs across, and then all our lateral lines and beds are going to the north and south along the field. In this example, we don't have as nicely laid out fields. Some of the fields are scattered throughout the farmstead. And in this case, we may have some underground main lines running to our frost-free hydrants at these different locations. And then the different irrigation zones each have a manifold hose and the associated laterals across the different beds. We want to take a moment just to talk a little bit about what conservation practice standard we're designing to and some of the associated practices that we're going to see in the field when we're also working with a microirrigation system. Microirrigation systems are designed under Conservation Practice Standard 441, Irrigation System Microirrigation. The systems that we're designing, we want them to be able to efficiently and uniformly apply that irrigation water and maintain the soil moisture for plant growth in that area, in that field that we're trying to irrigate. That system needs to be able to have the capacity to meet the water requirements of that crop during those critical periods of growth. You think, right, when it's in July and we have a really dry spell, that irrigation system needs to be designed to meet that worst case scenario. So when we're running this micro irrigation system, we may have really big zones or multiple zones, and we need to take into account that there's only so many hours in a day that we're able to physically irrigate the crops. And our design needs to ensure that the maximum time that we're applying water does not exceed 22 hours per day, or in a 1 week period, we don't have over 6 24-hour periods of irrigation. For the emitters themselves, we want to look to have and design with emitters that have coefficients of variation less than 0.05 for point source emitters and less than 0.07 for line source emitters. And these are specs that are going to be called out with the components that we're choosing in our design. Similar to all of our pipeline designs, to reduce the chances of water hammer damaging any of the pipes, we want to limit our flow velocities to be below 5 feet per second. And then lastly, a really good target that we want to hit is that emission uniformity, right? We want this micro irrigation system to uniformly distribute the water throughout the field so we're not having to over irrigate in certain areas to make sure that we're hitting that critical amount of water needed. And we want that EU to be designed for at least 85%. A common practice that we'll see implemented along with a micro-irrigation system is an irrigation water management plan under Conservation Practice Standard 449. And really what this plan is put in place for is to improve the efficiency that we're using irrigation water, to make sure we're not under or over irrigating, and knowing how we can manage that allowable depletion zone. Right, so we want to know the depth of water that we need to apply with the irrigation system based on the crop evapotranspiration, the monitoring of the existing soil moisture in the field, some of that computerized scheduling of what time of year it is, what growth stage that crop or forage is in, and then really monitoring of that plant. So there's a lot of things that can go into the complexity of an irrigation water management plan, but at the end of the day, it's a plan set forth to let us know when and how much we should be irrigating to more efficiently use the water resource available. A very common practice that we're going to be used with our micro irrigation designs in Ohio are high tunnels. Right, these high tunnels under Conservation Practice Standard 325 are utilized to extend the growing season of different crops that are being irrigated or grown in a garden setting, and protect them from any severe weather such as high winds or hail. So there's different types of high tunnels with different types of roof structures, such as gable or tunnel slash Quonset structures being probably the most common that I see in the field. And a lot of times the beds and micro irrigation system laterals will run down the length of the high tunnel. Giving some examples of where we may see components laid out in a high tunnel system. When we think of all those components that we talked about in a control head, you know, we think this may be big setup, but in a high tunnel system, really it doesn't have to be overly elaborate. We are able to have our filtration system, our chemigation ports, our pressure regulation, any, pressure valve, pressure gauges and valve, pressure relief valves in that control head, really all just in a linear fashion located at the front or just outside of the high tunnel. From there, we have our water supply running with our main pipeline, typically to a frost-free hydrant located either at the corner or up at the top of the high tunnel, that manifold tubing running across the top, and our beds and lateral lines stretching the length of the high tunnel, kind of like shown here in this example. As we mentioned earlier in our main and sub-main discussion, irrigation pipeline is pretty commonly practiced with irrigation systems under Conservation Practice Standard 430 irrigation pipeline, and that's for that conveyance and distribution of the water from the source out to those zones, out to the fields. And that standard is going to define the allowable pipe types and appurtenances that we need in that system. And then typically right in Ohio, we're using buried plastic pipe, and we're going to have that maximum flow velocity of 5 feet per second, protecting us from any damage from water hammer. Some items that may come up as we're needing to develop water sources or we're doing some tailwater recovery. Conservation Practice Standards 642 is for developing a water well, right? And this would be to establish a reliable water source where there isn't one existing currently on the farm, and to address that resource concern of water quantity. One thing that we discussed, right, we want to make sure per our existing guidance to perform that constant rate drawdown testing to make sure that the well is able to supply the needs of the micro irrigation system. And while we have limited use in Ohio, where we're really not designing many ponds, Conservation Practice Standard 378 pond could be, utilized to develop a water source for surface water. And there may be some expansion when using this standard under the newly adopted standard 447 irrigation and drainage tailwater recovery. If we need to install some sort of pump to energize the system, rather that be an electric or a solar pump in a well or a surface water intake such as a pond intake, Conservation Practice Standard 533 may be used to install that pumping plant. If we're installing a high tunnel as part of our micro irrigation system, we may need to then address some of the roof runoff coming off and out of this installed structure. This impervious layer is going to have a lot more runoff and potentially cause ponding or soil erosion around the high tunnel site. Additionally, some of this runoff may want to be collected or may need to be collected for on-farm use. Typical solutions that we're going to see to this is running a rock trench along the axial length of the high tunnel, and those rock trenches are going to be contracted under Conservation Practice Standard 558 roof runoff structure. In that rock trench, we'll likely have a 606 subsurface drain, a perforated pipe. From that perforated pipe, we'll then need to take that water and direct it to a stable outlet using an underground outlet pipe. And then we'll want to make sure we have some sort of protection of where that water is coming out to make sure that it's being stabilized. Taking a look at what you may be expected to draft on a set of engineering plans, we'll give some examples of details that are floating around the state. Looking at what the drafting requirements are for a micro irrigation system, some of the highlights from Part 541 of the Ohio Supplement. We'll want to make sure we have a plan view of the system that shows the zone layouts, the different bed layouts of that micro irrigation system. We need to identify the water source, have some sort of identification of what the minimum system flow rate requirements are to supply the microirrigation system. We'll want to have any details and the locations of those appurtenances we discussed kind of in the control head, right? Any valves, filter, pump, pressure regulator, etc. And then at that point, when we get into the actual microirrigation zone, we'll want to make sure the emitters and the laterals of those drip lines are sized appropriately and called out. Lastly, as with any other engineering practice, we'll want to make sure we have an associated quantities and estimated bill of materials for all those items in the microirrigation system. And then additionally, if we have any of those practices that were added on as part of our system, such as the irrigation pipeline, the roof runoff structure, and any of that subsurface drain or underground outlet, we'll need to follow those subsequent drafting requirements for those practices. Taking a look at an example plan view, we may have our source identified here. In this case, it's a connection to a rural water line, our irrigation pipeline, our main line running up and across our two high tunnels, which are labeled appropriately. And from there, we have our rock trenches on each side and the associated subsurface drain and underground outlets. Looking further at the first page of some microirrigation details, we're going to have description of what our microirrigation zones are, how many beds there are, their dimensions, and what tapes are being used. So some of that design data of how the beds are laid out, the drip tape specifications used in this design, additional requirements of what capacity is needed to provide the system, if there's any chemigation or fertigation used in the system, and a disclaimer saying other tape designs can be used and can be utilized to meet the specifications, and if we're purchasing different than what is designed in this system, just to contact your NRCS office so we can work through some of that changes in the design to make sure what's being installed is still going to meet the standards and specs. On this page, we'll also have our irrigation pipeline installation detail to make sure that we're being installed below the frost line, and then a frost-free hydrant detail as well to have proper installation of that frost-free hydrant at the top of the high tunnel. A second page of details shows some more zoomed in views of what the bed layout and what the lateral and manifold layout is going to be for each microirrigation zone. Firstly, we have some details about the control head requirements, calling out the filter, making sure we have a pressure regulator and what that is set to, leading into our manifold hose that distributes to our laterals. On the right, we have the high tunnel layout itself of the different beds, the bed spacing, where the manifold and hydrant are located in the high tunnel. And then here in the center is an example of a bed layout showing that we have two drip tapes, their spacing in each bed, and the length of those drip tapes. To the left, we're providing a kind of brief irrigation water management plan to let the landowner know, if we're experiencing the maximum irrigation requirements that we would need per month, this is the amount of time it would take for this irrigation system to water this zone. Looking into some associated practices, right, we talked about that rock trench being off of a high tunnel, so this is the standard detail page for that, showing the installation of the rock trench, some of the stone requirements and the sizing, installation of that subsurface drain, and then our underground outlet protection. And right, we'll want to make sure we have any profiles for that to make sure our pipes are put on the proper grade to have capacity. Giving some examples of how other states may be drafting some of their micro irrigation systems. Similarly, right, they're going to show their layout of their zone, their different bed layouts of walkways, and how many tapes per bed are being installed, your manifold pipelines and lengths and dimensions, your control head, all those appurtenances that are going to be installed in that system. So now we know all about the components and what goes into and what we need to design to for a microirrigation system. So we're going to discuss a little bit about what tools and resources are available to assist with designing these systems. Shown on this slide and linked in the PowerPoint are some examples of resources that NRCS Ohio is typically referencing in a microirrigation design. The National Engineering Handbook has sections on irrigation and specifically Chapter 7 on microirrigation that have a wealth of knowledge and example pictures in the design process and all the terminology further than what we discussed here in this TDP and are really good resources to look at. Similarly, the Engineering Field Handbook, Chapter 15 on irrigation is a good place to start. You could get some of those basics of what constitutes in the irrigation system design. The Irrigation Toolbox is kind of a separate website that NRCS has developed that references a lot of these uh, National Engineering Handbook manuals, but also pulls in some outside resources and is really just a good place to kind of search for information on irrigation design. And then lastly, really commonly used throughout our design process is we'll reference the Toro Microirrigation Owner's Manual and some of the design specs of the Toro systems. They're just very readily available and gives us a place to base our design in. Now looking into what goes through in the design process, we'll go through some example calculations and then Alyssa will demonstrate the design tool. It's always a good idea when we're going into a design to understand what's the objective, what's our end goal, what do we want to achieve with this design. So for a micro irrigation system, we want to make sure that we're designing a system that each plant receives the same amount of water, right? We have that good emission uniformity and we want that water to be in sufficient quantity, right? At the worst time of the year, can we provide enough water? And we want to make sure that it's doing that at the proper time, right? We're not irrigating for more than 22 hours per day. We're meeting the practice standard. And we want to do that as economically as possible. If we can do that with one drip tape per bed, why do we need to install 5? We want to have that in mind as well in our design of our system. And one thing that I always like to keep in mind is a good design is always elegant, right? It doesn't have to be overly complex. It doesn't have to be fancy. It's usually the simplest one, but it's fully effective and meets everything that you need to solve the problem on the site. There's going to be many criteria that we need to design and select in our microirrigation design to really meet the conservation practice standard. Just giving a quick overview of what some of those decisions are going to revolve around, right? We're going to need to be able to map out the fields, map out our zones, evaluate the site. What is the topography like? How is that going to impact our microirrigation system? And a lot of that's going to be handled, with that engineering survey. We're going to need to select our emitters to make sure that they are sufficient for the crop spacing. Those emitters can provide the necessary flow rates we need, but that emitter is not going to require a flow rate such that the source cannot supply that water, right? We'll need to determine what flow rates do we need in our system to replace that peak daily evapotranspiration from those plants, right? In that super hot month, we need to have the capacity in the system to supply the water needed for the crops. As we discussed earlier, we'll need to evaluate what our water source is. What quality and quantity of available water do we have at what flow and what pressure to supply our system? And then getting into actually designing the zone and the layout, right? Matching everything of our emitter size and spacing and how many lateral lines we have per bed and those size of those zones to the supply, flow, and pressure. Sizing any pipe along the way for main lines or sub mains, and then the placement of all those appurtenances, such as the pump in the pump house or any valves. In that full design of all that water flowing, we'll need to ensure that our hydraulic calculations of the flow, pressure, and the friction loss all work out. And then lastly, we'll need to select and size a pump and the proper filter for our system. So the process of going through a microirrigation design can be taken from few different avenues. The one that we're going to present today is walking through, identifying your source and your source capacity. That's a good place to start. What can I do? What water source do I have on site to work with? And that's going out in the field, taking pressure readings, evaluating any sources there, doing your desktop investigations of any well logs on the site. From there, you'll need to estimate your zones and bed layouts. How does the producer want to irrigate this field? Are there existing fields and beds, or how are these fields and beds located in proximity to the different sources, and what are the capacity of that single or those multiple sources. From there, it's a good idea to determine what our peak evapotranspirations and then therefore our irrigation water requirements are going to need to be for each zone. That's going to be based on, right, that irrigated area and that crop ET, peak ET in the summer. From there, we can take all these values and go into the hydraulic design of each micro irrigation zone, and that'll take into account the sizing of the tapes, evaluating our emission uniformity, and determining how long it is going to take for each zone to irrigate. And from there, as with any good design, you're going to need to iterate. And that's what these tools that Alyssa is going to discuss come into play, is they give us the flexibility to change things around instead of needing to run all these calculations over and over and over. And we can really massage that design into something that works well for the producer and meets the conservation practice standard. Along the way of this design process, a good thing to do is estimate your crop water needs, and that can help you with evaluating your source and selecting your emitters down the line. So we'll give an example problem here. So we want to calculate the capacity required for a 1-acre microirrigation system for vegetables. Let's say those vegetables have a peak evapotranspiration of 0.2 inches per day. We're going to give some information of what drip tapes are being planned, how many rows, what spacing the rows are, how many zones there are, etc. And we want to design for emission uniformity of around 90%. So we can take the equation here to calculate the required water source capacity in gallons per minute. We can take 453, which is just a conversion factor, right? This is just kind of a rough estimating calculation, times our depth to irrigate, right? So how much water do we need to apply to the field? Well, we need to apply our peak ET divided by the efficiency of our system. So that peak ET divided by our design emissions uniformity, at this case, is 90%. That's just a good target number to hit. When we come back into the actual design with the actual tapes that we selected in the true bed layouts, our EU may be a little bit higher or lower, but this just gets us in the ballpark for selecting our tapes. The area irrigated in acres and the time that we want to irrigate. So for this problem, we plug all that in. Let's say we can irrigate by the standard up to a max of 22 hours per day. The flow rate from our source that we should need to expect is 4.6 gallons per minute at minimum, right? And some of this can change later on when we get into the design, and some of these knobs we're able to turn, we can adjust what actually the system needs to be able to supply. So from that last slide, you may ask, how do I determine my peak evapotranspiration and then therefore my required irrigation water requirements? How much water do I need? Well, there's a couple ways to do it. You may have floating around your field office or your area office this Ohio Irrigation Guide developed by the NRCS, and in that there's some peak evapotranspiration tables for common crops that we're going to be irrigating. Or recently developed is the irrigation water requirement spreadsheet, which is able to look by county across the state and does the same thing. Takes into account what crop we're trying to irrigate, the growing season, and estimates your peak daily ET required for the crops. At some stage along our microirrigation design, we're going to need to select the emitters and the laterals that we're going to be using in design. It's always good to contact the producer and understand if they're already working with a local irrigation company or supplier, or if they're frequently using a different type of tape. They may oftentimes not know what tape they want to select or where to go. And at that stage, right, we have a little bit more flexibility of sizing and selecting probably the most appropriate size tape for their application. So this is an example of some drip tapes that you may see and utilized in some of your designs. So we have on the left just the manufacturer's number, right? There's different emitter spacings. A very common one that we'll utilize in Ohio is 12-inch spacing. These drip tapes can be operated at 8 or 10 psi, right? So this first table is just the emitter flow rate. So at 10 psi, this specific drip tape has an emitter flow rate of 0.22 gallons per hour at each emitter. but then along the tape, the drip tape has a flow rate of 0.37 gallons per minute per every 100 feet of tape, right? So if there was 200 feet of tape, it would be twice as much. It would be 0.74 gallons per minute is being put out by the tape. The emitter exponent is used in part of the design, and there's some additional, information here of what filtration requirement is needed. So when we're sizing and speccing our filter, all this should be taken into account in our design and in our drafting. And before we get into utilizing some design tools, it's good to have an understanding of what is going on in the background. What are the zone hydraulics for the pressure and flow rate of our micro irrigation system design? And it wouldn't be an engineering TDP without a little bit of math. This is going to be our example for our zone hydraulics problem. So right, we have our main line here, teeing off to our manifold tubing. From there, we have all our lateral lines, and each of these tick marks is representing an emitter on each lateral. Right, so to go over our goals of what we're trying to achieve with the design, we want to deliver, right, equivalent amount of water to all of the emitters. We really want to try to minimize the costs of the pipe, right? We want to reduce what our friction losses are, which is going to impact our pipe size. We want to reduce the pressure variation between these emitters so that they're all more equally and evenly distributing that water, right, to get that good emission uniformity. We need to allow for the zones and different crops to be turned on and off. So how we're structuring our zone sizes, right, that may take into account where there's shutoff valves or how big our zones are. And then we want to make sure our lateral lines and those emitters are lining up with the existing crop rows and the existing crop planting spacing. And then lastly, if we're placing any manifold tubing or main lines, we want to make sure those are conducive to how the operation is running and they're not going to be obstructive to equipment operating throughout the fields. So the first thing we're going to talk about with our zone hydraulics is our emitter flow rate, and then ultimately what our zone flow rate is needed coming into the zone. So when you remember looking at those example emitters, the flow rates for each emitter were in the tenths of gallons per hour. For this example, we're just going to assume each emitter has a flow rate of 1 gallon per minute, which it just will make the math a little bit easier for us walking through this. So at each emitter, we're going to have 1 gallon per minute, right? So when we go to the next, this pipeline needs to provide 2 because it's going to be 1 here and 1 here. Up the emitter again, we're going to add the more flow rate needed, so 3, 4, 5, 6, 7. And each lateral line coming to it, we need to supply 7 gallons per minute to make sure that each emitter is outputting 1 gallon per minute. Then summing across each lateral line, right, we have 7, 14, 21, 28, 35, 42, 49 gallons per minute. So from this main line, we need to have 49 gallons per minute entering this manifold tubing. Similar to evaluating what flow rate needs to come into the micro irrigation zone, we also need to establish what pressure is needed at the inlet to the manifold for the design. So for each emitter, we're going to assume that it has a 5 psi operating pressure. So it needs at least 5 psi at each emitter point to operate properly per the manufacturer specs. So then along each stretch of pipeline, so each lateral pipe between the emitter, we need to account for what is our friction loss in that stretch of pipe. Well, using the Hazen-Williams equation and taking some assumption of our pipe diameters half an inch, our Hazen-Williams coefficient is 150, and that we have 10 feet between each point, so between each emitter. We can come up with that for each section. For this first one, we have 5 psi, and that friction loss comes out to 0.12 psi, right? And then for each subsequent emitter, the flow rate is increasing, therefore we're going to have a greater friction loss. We get to the end of the lateral, we sum then across our manifold hose and get to the little stretch from our manifold, our first lateral, to the main line, and we see that we need 517 psi. So from these two things, we've identified that our source needs to provide 49 gallons per minute at 517 psi. And remember, the emitter flow rate that we used was just an easy 1 gallons per minute. But this process is what goes through in the design process for your micro irrigation zone hydraulics. So doing that math over and over again and trying to iterate a design would become very cumbersome and complex. Therefore, there's been some design tools developed. There's a couple NRCS spreadsheets out there. There's an older spreadsheet that walks through all of the block hydraulics for your micro irrigation zone. There's a newer version of the spreadsheet which looks like this, and Alyssa will be covering that throughout the remainder of the presentation today. There are also some state level spreadsheets that do some of that background calculations. And there's also a software called IRRCAD that can be utilized for really complex micro irrigations and can be integrated into the CAD software. Hope everyone's still following along just fine. We wanted to take just a few minutes here, and a lot of those slides were recycled and kind of revamped and reused from a training that was given out by some NRCS folks late last year. And we just wanted to say, thanks to those for all their help. Some of the individuals were Kelly Scott, Hamid Farhani, John Chilcote, and John Hester. And I think Kelly's actually even on the call today to help with any questions as we get into some of the design spreadsheets. So really appreciate all their help and providing those resources. So we're going to go through a quick 5-minute break / Q&A here. So Alyssa will transition into her slides and get those started around 10:22, which is 5 minutes from now. In that meantime, feel free to throw more questions in the chat. And then there's been a couple questions that I've responded to, and I'll go through and read what those are and answer them. That way they're on the recording, and everyone can hear those when it's posted to the YouTube channel. So the first question was, can we get access to the PDFs of the slides, mainly focusing on those small scale irrigation examples? I think the plan is to provide the slide deck as a PDF, and there was the one slide that had a couple of links to those resources, so that way you can just click on the link instead of having to go find it yourself. I think the plan is to distribute that. Alyssa, you can correct me if that's wrong or different. Okay.
Hey, Logan, Alyssa just stepped out.
Okay. I'm pretty sure we're planning on sending it out. And if not, you can get a hold of me directly and I can share it with you with no problem. So I'll throw my email in the chat. That way everyone make sure they have it. The second question that was posted was, so what do we do or what's the alternative, or what do we do when there's not a water source right nearby? So, right, the first kind of option, and usually the typical thing we do, is you're going to have to transport or develop a water source. So if we're in a really rural area, that maybe doesn't have a municipal water supply, we're going to maybe need to develop some sort of well, develop a spring, have a storage water tank to store some of that water in an underground cistern. At that point, we're then going to need to install that pumping plant and pump that through some irrigation pipeline to get it where we need to irrigate where our high tunnel is going to be located. There may be even situations that I've ran into that, and Alyssa's actually ran into a couple projects where there isn't a water source on site. We have a pretty small site. It's rural, very remote. There's no county water. It's a small property, only, a couple acres. So we don't really have the space to develop a spring. The wells on site maybe don't have the capacity available to supply all the water needs for the irrigation. So in that instance, something we can look into is collecting some of the surface runoff that's coming off of that high tunnel. And while you can get sometimes the design to work out and some of what you need to supplement the water already on site in those low capacity wells, you're right. You have to think the months that we're going to need the irrigation the most is going to be our July or August in Ohio when it's really hot. But those are also going to be the months where we're going to have the lowest rainfall. So you're kind of at your time when you really need it and it's most critical, you're probably going to have your biggest risk of not having available water supply. So just some things to work out. If you run into those situations, definitely get a hold of your NRCS engineer, your OD engineer, and we'll come out and help evaluate and address accordingly. And then there was another question about, so for a producer who has a high tunnel and is interested in micro, is it necessary for the engineer to design the micro irrigation system, or can the producer design and install the system? I'm going to answer that question as, right, whatever we're designing and constructing, if it's through an equip contract, it's going to be required to meet NRCS standards and specs. Most time, yeah, right, that project's going to come to us, your NRCS engineer or CET, your ODA engineer, or one of the soil and water staff is going to take on that design, work with the producer, and then someone with engineering job approval authority is going to sign that. There are options that projects can be completed by external licensed individuals. So, licensed engineers, if they're meeting the statement of work for those practices. I would say though, for high tunnel designs, you're probably on the smaller side of an irrigation design, and the cost to source one of those licensed individuals may not be worth the expense of what you're going to get benefit wise. And I think the better way to think about that question is, right, there's oodles of options. We showed all those different drip tapes of just one manufacturer, and that's just drip tapes, not even point source emitters or micro sprays and etc. So there's all these things you can choose from. It's really important on your site visit to speak with your producer and understand what size high tunnel they're installing, how they want their beds laid out, what are they growing, right? Know if I'm going to go down the road to buy my micro irrigation supply, I'm not going to purchase something all the way over in Cincinnati. So if we know kind of what they have in mind of using already, we can gather that information, design their beds accordingly, and then also design a system that's going to meet standards and specs. So I think a lot of the high tunnel designs and situations, NRCS, ODA, and the soil and waters, probably the best route for the producer is just to work with us to develop that design to kind of what they need. Steve with the fun question of, can we capture water from a roof runoff structure and store it in a tank to use for micro irrigation? And can EQIP provide funding for the storage tank? We can. Yes, you can do that. That goes back to the question above of situations where, how do you handle when you have no other water source, what are something you can develop, and how we were discussing, you can collect some of that roof runoff. So it can be done. It should probably never really be our first option to look at in choice. It's something a lot of producers may be interested in as a supplement kind of to their existing system, or maybe we're installing a system through Equip off of a rural water tap. Them implementing the tanks on their own and collecting some of that roof runoff on their own is, right, you're taking into mind how their fiscal operation is going to work. But that's not going to be the most reliable resource, right? And NRCS and Equip sets out to address the resource concerns on the site. So if we're only solely, relying on this roof runoff, when we get to those months of July and August, that there's probably a chance for some problems. So we can do it. It's just take all those design considerations into account. And then Steve's asking if Equip can provide some funding for those storage tanks. Again, I think when it comes to those really challenging sites where that's the last option that we have available to make work, I think Equip can step in and assist with that, but that probably should never be the first option that we're choosing, or we're directly going to, yes, we're installing storage tanks on every high tunnel and every micro irrigation system that we're designing. So, Steve, did I answer your question?
Yeah, thanks, Logan.
Okay, so I think that's all the questions we have. I'm gonna turn it to Alyssa, and she's gonna take it the rest of the way there, and I'll be on standby. And feel free to throw more questions in the chat.
Thank you, Logan. Yeah, Logan will be manning all of the questions in the chat. But moving forward, Kelly Scott is also on here for questions with the spreadsheets as we're going through this design example. So. Alright, so I'm going to be going over the design example for today, but before I get into that, I wanted to talk about the first step for any design, and that's going to be our information gathering. So the document shown here can actually be found in ePhotog. If you go to the Conservation Practice Standard 441 section, this is just the general planning document. First few pages of this document are going to go over general microirrigation information like Logan has gone over already in the previous PowerPoints. And then our last few pages are going to be this general planning. So this guide is meant to be something that you can reference while you're doing your information gathering, whether it be in the office before a site visit or while you're out on the site visit. If it's your first time doing a microirrigation design, then this guide might be beneficial for you to take out on the site with you. And then as you get more comfortable with doing these designs, you're going to get an idea of what information you will need for the design process for your site visit and can get away from using this. Alright, so here's just some of the main information that you want to make sure to gather while doing a site visit. First, what are your potential water sources? In some instances, the water source that the landowner wants to use might not be adequate to supply the system that we are going to be designing. So, you need to consider, does their well have water quality concerns? Does it provide the minimum flow rate that's needed to operate the system? Do we need to look for an alternative source of water? Does their pond have water quality concerns? Or is it just not feasible to use? Are there quantity concerns? Does it dry up in the summer? And then generally our main concern with the rural water is just going to be what is the pressure for the system and will we need a pressure reducer? So you just want to make sure that you can understand what options might be available on that site in case you need to switch your water source during the design phase of the project. So if a producer says they want to use their well, maybe have a backup option while you're out there so that you don't have to go out there multiple times. Next, you'll need to know what crop they're growing. Are there going to be multiple types of crops? Are they going to be doing some sort of rotation, etc.? You want to know this so that you can make sure that we're designing the system to meet the maximum needs of any plant that they're going to have in the high tunnel. And then next we'll want to know what is their desired high tunnel layout. Where do they want their hydrant to go? What size beds or walkways are they planning? How are the plants going to be spaced? Do they know how many drip tapes they want per bed? Or do they want us to design it for them and tell them what we think would work best for the scenario? Lastly, do they know what drip tape or system they are planning to purchase? This would be beneficial for us to have when we go into the design phase. We can go ahead and design the system for this exact tape that they're going to use rather than making an assumption and having to as-build later based off of the specific one that they purchase. And then while you're out on the site, you're also going to be taking a topographic survey of the area for the high tunnel to identify your slope of your zone, the slope of the beds, as well as get your survey points that are appropriate for whichever water sources you will be analyzing and the pipeline that will be going to the tunnel. So for our example problem, we're going to be looking in Ross County. We're assuming that a producer has a equip contract already for a microirrigation high tunnel design for a 30 by 50 high tunnel. And we have the information that we gathered during the site visit. We know that there's an existing well on the site, and if the well doesn't work, the landowner is willing to add in a tap for the rural water if it's necessary. They're planning to grow mixed cut flowers with 4 5-foot wide beds, 2-foot walkways, and 4 tapes per bed. We know that they want to have their hydrant located in the top right corner of the high tunnel, and when we got back in the office, our survey showed a slope of 1% across the length of that high tunnel. So the first thing that we're going to need to determine is if our well is going to be able to provide enough water for our system. If the landowner is not aware of the flow rate of their well, we might be able to look on ODNR's water well database to obtain a well log. So So to determine if our water source is going to be adequate, we can determine our minimum flow rate needed for our system quickly with this equation that Logan had gone over in the previous PowerPoint. So first we're going to be obtaining our Q, which is our system capacity in gallons per minute. This could also be considered the flow rate that will be required to meet that peak crop water demand. And then we will be using our irrigated area, our application depth, and our time to irrigate. First, for this, we're going to go ahead and solve for our irrigated area in acres. So, although we know that in our high tunnel we're going to have walkways and the whole high tunnel isn't going to be irrigated, for this quick check of if our water source is adequate, we can go ahead and just use the entire area of that high tunnel for our calculation. So we'll do 30 foot times 50 foot and get that 1500 square foot and convert that to acres, and we'll get 0.03 acres, which we will go ahead and fill in our equation here. And the next thing that we want to obtain is that application depth, which we will actually need to go to our irrigation water requirements spreadsheet to obtain. So once you have that spreadsheet open, you will start out on this climatic database tab, and we're going to start out by selecting our state, which in this case is Ohio, and then our county, which we know is Ross County from our example problem. And then you'll select a weather station for your project. Most of our counties will only have one weather station. However, if you do have a county that has multiple, you'll just pick whichever one is closest to your project site. So we'll go ahead and fill in that one, and then you'll want to pick the most recent data range that you have for that weather station. In this case, we have 1981 to 2010, and that information is going to automatically populate in our table with our min, max, and average temperature and our average precipitation. And then over here, you're going to choose whether your weather station location is interior or coastal. So for most of Ohio, we're going to be interior, but if you live up by Lake Erie, where your air masses might be influenced by the lake effect, then you could select coastal here. But for our case, we're in Ross County, we'll be choosing interior. So you'll see that it's asking for height of weather station, and this is a typical number, the 2 meters for our weather stations. However, we don't really have a different number to put in here, so we're just going to leave it at that 2 meters. And then down below, you'll see that we have 30-year monthly averages for our solar radiation, sunlight hours, wind speed, relative humidity, and all of these variables are not collected by our selected station, so none of that data will populate in this table, and that is perfectly okay for our design purposes. So that table will remain blank here and on the report printout, but again, that's okay. And then, of course, you'll want to input all of your job information here. And then going on to our crop coefficient tab. So this is looking at multiple different curve types. We have the basal, the Blaney-Criddle, and the FAO curve types. And there's also an option to input your own crop information if you have it. So you can come in here and type in your own and then come back and select that. So we don't really have any other options here for a mixed flower case other than to use sunflowers. We don't have any other data for flowers, so we're going to go ahead and choose our FAO crop curve, and we will pick our sunflowers. If you scroll through here, you can see there's a lot of different options. So sunflower can either be irrigated or rain-fed. Obviously, in this case, we're going with irrigated. And you could see from some of these other curves, there's a lot of different crop types that we have data for, so you'll just pick whatever is closest for your project. So then it's going to ask us a condition for some of these, and for this case we're going to choose Mediterranean because that is the only option that we have. Some of the crops are going to give you the option to choose tropics, and since we do not have weather that is similar to the tropics here in Ohio, we are obviously not going to have that different plant date or something that they would experience in the tropics. So we're going to choose Mediterranean in those cases as well. And then moving on, we are prompted to input our start and end dates. This spreadsheet does not like to go into the next year. So if, for example, maybe you are planting in October. I'm just making these up. So October 2025, and you're going to harvest in February of 2026. So you can see here over in this table that it populates our October through December data, but it doesn't populate January and February, and that is because this is pulling based off of the day of the year. So once you go past 365 days, it's not going to populate your data. So for our scenarios, we can typically just leave this as January 1st to December 31st, and we will have the entire table filled out and then just use the information that is pertinent for our design. And then similarly, if you've chosen to do hay, you can have your hay cuttings and dates down here. And then the next option is going to be to input our irrigation and soil moisture data. So it's going to ask, are we using carryover in our soil moisture irrigation budget? We will select no, because when we have a high tunnel design, this is going to be an isolated system that is not going to have any soil moisture carryover from precipitation. So we don't have any additional moisture in the soil. We are needing to add all of the moisture that we can to supply these plants with the water they need. So looking at our net irrigation depth that is applied to each irrigation next, we'll find that our value here should not go below 0.75 inches for this spreadsheet. So we're typically going to end up leaving 0.75 inches here for our designs. We can get the actual net irrigation depth applied from our next spreadsheet for the microirrigation design, but typically we will see values that are less than 0.75 for our designs here in Ohio. So we'll leave this here. And then for our soil water storage, this 2-inch value is representative of 40 to 60% of available soil water capacity in the crop's root zone. So we'll actually be able to get that exact available water capacity from our next spreadsheet as well, and we could come back here and compare that. But since we're designing for a high tunnel, this value is not going to matter for our design, since the only factor that this is influencing is going to be our effective precipitation, and since we are in a controlled environment that won't be influenced by the rain, we won't need to worry about what our effective precipitation is here. So we can just leave that 2 inches for this design. And finally, we'll go to our report tabs, and you will want to print out each of these reports to put into our final design folder. So this first one is the climatic data summary tab, and you'll see that we have our monthly evapotranspiration, and this number is multiplied by our crop factor, which you'll see on the next report. And then we have our effective precipitation and net irrigation requirements for a dry year versus a normal year. And you can see that this value is taking our total monthly evapotranspiration multiplied by our crop coefficient and subtracting out our effective precipitation that we'll be able to use for the crop, and then giving us what our net irrigation requirement would be. But again, since we are in a controlled environment and won't be using any of the precipitation, the only value that we really worry about here for our design is going to be our peak daily evapotranspiration. But you'll print this out and you'll put it in your folder. And then our next report is going to be crop data details, and you'll see here that it gives you average temperature and precipitation for each month, and then also displays that effective precipitation from before. And then here's where, if you had input any carryover for the soil moisture budget, it would show up in here. And then here is your evapotranspiration and that crop factor, where these values are multiplied to get that total monthly evapotranspiration we saw in the last table. And then here you see that same peak daily evapotranspiration. So then you'll print this report out and put it in your folder as well. And then our report 3 is job crop summary, and this is going to show us information from our weather station. It's going to show our mean temperature, total precipitation, effective precipitation for each month, and then down below for your specific crop, it's going to show you your net irrigation requirements based off of your effective precipitation for dry versus normal year, as well as your peak daily irrigation requirements. So you'll put this in the folder as well. And then our climatic data input tab, you're going to see that it's giving us some temperature and precipitation data again. And then this is where that wind, relative humidity, and solar radiation data from that first tab would populate if we had that. And then this last tab is our irrigation water requirements summary. And you'll see here that it gives you reference evapotranspiration for grass, what your crop coefficient is, what your crop's evapotranspiration is, your average daily evapotranspiration, and then that peak daily evapotranspiration. And this is the number that we really care about for our design. So we're going to come and we're going to look at, okay, we have our peak of 0.29 inches. That's occurring in July. We can assume that they will have their crops planted in July, so that's what we're going to design on, the 0.29 inches of water need for our plants. And then it also populates your precipitation data in here as well. So print out each of these reports and put them in your design folder. So now that we have this value of 0.29 inches, we can go back to our PowerPoint and fill in the rest of our example problem here. So our application depth, we're going to take that 0.29 inches and we're going to assume a system efficiency of 85%. So our net application depth is actually going to be this 0.34 inches. So we'll go ahead and fill that in here. And here you can use 90% efficiency if that makes you more comfortable. I'm just going with the 85% since that's our minimum system efficiency that we would need to have. And then our time to irrigate, typically for our smaller high tunnel systems that we are designing, we want to try to supply all of the water needed to the plants within 1 hour or less. So plug in 1 hour here and we will find that roughly we need to have a flow rate of 4.62 gallons per minute to supply our system. So we need to determine if our well potentially can supply this 4.62 gallons per minute flow rate. So we can go over to our ODNR website to see if we'll be able to find an approximate flow rate or the well log for this specific well. So you can find this database with a quick Google search, and then you'll come into the interactive part, and you can, if you have your county, street name information, go there, or you can just zoom into your site if you know where that is. So our site is going to be right here, and we can see that there is no blue dot that would indicate that we would have a well log for this specific property. However, we can go and look at some of these wells that are around and get an idea of what kind of flow rates the wells have in this area. So this one next door has a test rate of 20 gallons per minute. Down the road here we have test rate of 10 gallons per minute. Then up here we've got 20 gallons per minute, 20 gallons per minute. So for our design, we're going to assume that this well is going to supply anywhere between 10 and 20 gallons per minute. So with our needed 4.62 gallons per minute, we can say safely that this well will supply the amount of water that we need for our system. And this is definitely not to say if we had a well with a flow rate of 1 gallon per minute, it absolutely will not work for our system. We would just have to increase our time to irrigate to greater than an hour, so that we would end up with a lower flow rate that is needed. So you could play with the equation. If you know the flow rate of your well, you could plug that in here and kind of see, well, how much time to irrigate would you need for that specific well. So we're going to go over to our web soil survey, and you'll go through the process to locate your site and map out your area of interest. And then once you have that, you'll go to the soil map, and it will give you the map unit names for each of the soils found within your area of interest. So we know that our high tunnel is going to be in this Kendallville Silt Loam area here. So we're going to go ahead and just input that information for the manual entry here. So you'll type in your soil name, and then over here you'll have a drop down where you're going to select your soil texture. So we know this is a silt loam, so you'll put that in. And then here it's asking us for upper, lower limits as well as our available water capacity. So in order to find this information for your soil, you're going to go over to the Soil Data Explorer, and you are going to hit Soil Reports. And then you will scroll down here to go to our soil physical properties, physical soil properties, and then click View Soil Report. And then once that's loaded in, you can scroll over and down, and you'll see here that it lists our depths as well as our available water capacity for each of those regions. So upper limit of this region would be 0 inches, and then it goes to 6. And then our available water capacity is between 0.18 and 0.24. So we're going to go ahead and make an assumption of 0.21 here. And then you'll see from 6 to 7 we have the same value. And then from 7 to 30 we go down a little bit to 0.11 to 0.16. So we're just going to make an assumption of 0.14 here. And then from 30 to 34, it is the same value. And from 34 to 60, we bump down a little bit more to a cap of 0.15. So we're going to put 0.13 here. And then you can see as you were populating each of those data entries, our total available water capacity in the soil layer populates over here to the right. And then down below, you're going to have to find each of these. So in order to find your inhibiting layer depth for your soil, you can hover over each of these notes as well, and it's going to tell you exactly where you can go in Web Soil Survey to find this information. So for our inhibiting layer, we're going to our Soil Quality and Features tab. Go to Soil Features, View Soil Report, and we're going to come over here, and you see here that there is no restrictive layer for the Kendallville Silt Loam. So if you go back and read this note again, it says if the inhibiting layer is below 5 feet, leave the input cell blank, specify the depth, or input 5 foot. So since our soil profiles end at 60 inches, we're going to go ahead and just input 5 foot as the inhibiting layer. And then for the water table, same thing within the note. It gives you where you need to go to find this information. So we're going to come back over here and go to our water features and view soil report. Alright, and And once you have that loaded in, you can come over here and see where your water table is within that soil. So for our Kendallville silt loam, our water table is not populated here, so we're going to go ahead and just put 5 as well for this entry. Alright, and so now before we go on with what the rest of the spreadsheet shows, we're actually going to go ahead and show the automated method. So once you have switched your method over to automatic, you're going to select your state, you're going to put in your county, and it'll automatically populate in this area symbol. And then you'll just need to input your map unit symbols, which you would have gotten from your soil map over here. And this is case sensitive, so you want to make sure that you are matching the capitalizations and lower cases as they are shown on Web Soil Survey. And then once you input those, you're going to go ahead and hit Get Soils Data. And this might take a couple of minutes to load because it is pinging over to Web Soil Survey to pull that data into the spreadsheet. And once it has fully loaded in the data, you'll get this pop-up that says Soils Successfully Loaded. So you'll hit OK, and then you come over here and you choose what soils you want to denote as 1, 2, or 3. So we'll pick our Kendallville silt loam as our soils 1. And you see all of that information that we had input from before automatically will populate in now. Alright, and so then all 3 of your soils are in here. You can see it also automatically populates in your depth to inhibiting layer and water table. So now down here, it's going to ask what soil you want to select for your design. In this case, as we showed, this Kendallville silt loam is going to be the soil where our high tunnel is located. If you have a 50-50 split here, you can choose between the 2 soils for what to move forward with for your design. I would recommend going with your more limiting soil layer so that you are planning for that area of the high tunnel that might be in the soil layer that doesn't have as much available water capacity as the other layer. But it's up to you on how conservative you want to be with your design approach. So you would just select from this drop down if you're going with soils 1, 2, or 3. So here we're going with soils 1. And then for this layers classification, you're going to choose between the homogeneous, stratified, or layered classification for your soil. So you can see when you hover over here that it's going to prompt you to go to our tables tab with the emitter table 1 for more information here. So you come over to your tables tab and we see our emitter tab tables, table 1. It's going to give us a table showing homogeneous, stratified, layered based on soil texture and root depth, what our estimates of the wetted area are. If you look down at this second note underneath this table, it's going to say most soils are layered. So we know that most soils are layered, but you can find that information when you go back to your Web Soil Survey. If you look at your soil profile and you see it goes from silt loam to clay to regular loam, whatever it is, if you have that variation between layers, then you have a layered soil. But if you want to take a more conservative approach with your design, you can go with this homogeneous option, and this is going to be less wetted area based on your type of soil than if you had a layered soil. Now, the stratified soils, we're typically only going to use those when we're in a floodplain, since those soils are caused by the alluvial depositions and sedimentation, which would only be common in our floodplains. So for our design here, we're going to go ahead and be more conservative, and we're going to pick a homogeneous classification for our soils. And then over here we have our rooting depth, and if you aren't sure of your rooting depth for your specific crop, there is another table in that tab under table 5, which we can go over there, and it's going to show you various rooting depths for different crops. So you can look through here and find your specific crop, and that first column is going to be your rooting depth in feet. So, if we come down here to sunflower, we see our rooting depth is 4.5 feet. So we're going to come back over to our soils tab, input that 4.5 feet, and it's going to tell us what our total available water capacity for the root zone is, which here it's 7.85, and you can see that in our soil layer here, our total available water capacity is 8.63. So it makes sense that we would have a lot more available water in our root zone of 4.5 feet. If we were to change this to a 1/2 foot rooting depth, you see that we drastically lower what our total available water capacity is. Or if we were to say select soil number 3, where our available water capacity in that region is going to be less than it is for our Kendallville silt loam. So we're going to go back to our soils 1 for the design, and then we'll move on to our crop tab. So we're going to fill in our system parameters based off of what we found when we were doing the equation in the PowerPoint. So our irrigated acres, you can either do acres or square feet here. We're just going to go ahead and do square feet because I know it's 1,500. And then our Q, that's going to be what we found to be the flow rate at the source, which in this case we are assuming that 20 gallons per minute. And again, if you weren't able to find a well log or anything like that, you would be able to perform the bucket test that Logan had shown during the PowerPoint to get a gallons per minute estimate for that water source. And then here we know that our landowner told us that they have a pressure of 60 psi. So you would input whatever the pressure is. If the landowner doesn't know their pressure, then you would take a pressure gauge to, if they have a hose spigot or hydrant or something like that, you would go ahead and use your pressure gauge to get the pressure to input here. And then over here to the right, we go into water quality information. So you're going to select your water source from this drop down. In this case, we have a well. And then it's going to ask about the electrical conductivity of that irrigation water. Now, this is generally only a concern in areas where we're going to have that higher salinity. So unless the landowner knows of water quality concerns, or if you know that there are concerns for that specific area, then we're going to go ahead and leave this blank, and we aren't going to input any water quality data here. Now, if you are going to input water quality data, there is a water quality tab in this spreadsheet. It is hidden, so you'll have to right click down here and unhide it, and it's called WQ. So then when you open that up, you can go ahead and input all of your water quality test results if you had the landowner complete one, and it's going to tell you if the hazard level is small or severe based off of their quantities that they have from their test. And then down here it's going to tell you why each of these conditions are of interest for a microirrigation design, so you can go through that if you'd like to learn more about that. But for our case, we're going to say that we don't have any water quality concerns for our project. And then down here, you're going to select your crop type from the list. Here we see sunflowers, and it will automatically populate in our management allowed depletion, the allowable electrical conductivity for a specific plant, so that's the threshold that that plant can handle, and then the root zone or root depth for that plant. So we'll go ahead and delete these out since we are just looking at sunflowers. And then down here, if you did have multiple plants, you're going to select what you're designing to. So you would select maybe your most limiting plant, or whichever one you're going to have majority of, or maybe you complete multiple of these spreadsheets if they're operating on rotations from year to year. So in this case, we only have one crop type that we're considering, so we'll just put all of that information in down here. So then we see over here that it gives us the same total available water capacity as we had on our previous tab, but now we know that our management allowed depletion is going to be 50%. So we can only ever use 50% of the available water within the soil before we need to start irrigating again to keep our plants from reaching that wilting point as Logan had discussed previously. Then next we're going to scroll down and it's going to ask for our crop evapotranspiration estimation, and this peak daily evapotranspiration is the same as we found from our previous spreadsheet, the irrigation water requirements, and this will be our peak daily evapotranspiration that we found for July for the sunflowers of 0.29 inches. And then moving down, it's asking about inefficiencies here in leaching requirements. So we know that this spreadsheet is considering worldwide climate data. So here for the climatic type, you can choose between arid or humid. And when you go with humid, it actually increases that transmission ratio to account for deeper percolation, which is typically found in more humid environments like the tropics rather than the states. So for our projects, we're always going to put arid here. Leaching requirement, this would come into play for your electrical conductivity data, and if there are any leaching requirements for the soil for that. And then it's going to prompt you to select an emission uniformity. And this is the one that we need to be greater than 85% for our irrigation designs based off of the standard. So you can make an assumption here, and that can be anywhere from 85 to 100%. We're never going to have 100% emission uniformity, so we're going to assume 90% here, but if you feel more comfortable starting with a different value, then you can definitely do that. And you can always come back and change this later once you've filled out more of the project information and have a better idea of what your emission uniformity is going to be. So then all of this information is going to give us our irrigation system efficiency. And we can say here that this is the value that we will use to determine what our gross application value is. So we would divide our 0.29 inches by this efficiency to figure out how much we actually need to apply in order to supply that 0.29 inch demand for the soils. So next we're going to go on to our emitter tab, and up here it's going to prompt you to select your emitter type, and for this project in particular we're going to be choosing a drip tape, so we'll stick with this hose/tape option. But if you know that your landowner is going to be using a drip emitter or a sprayer, or if that's the design choice that you've made for your project, then you can go ahead and select one of those other emitter types. As you can see, our soils information has automatically been brought in from the other tab, and then it's going to tell us what our wetted diameter and recommended emitter spacing is based off of our soils information and the specific emitter that we have selected. So it's telling us that that emitter can supply a wetted diameter of 4 foot. So you can see here what that wetted area looks like. So we would have 4 foot across for our specific emitter in our soil. So then down here, you're going to be determining what your percent wetted area is based on the layout of your high tunnel. So I have sketched out a basic setup for our design example problem here, and you can see that we have those 4 drip tapes or laterals in each bed, and we have 4 beds. So this is all based off of what the landowner was planning to do, but if your landowner doesn't know what layout they had wanted for their high tunnel, then you can just make some assumptions and play with what works best for your design. So back to our spreadsheet. We can see it's prompting us for our row spacing, and it says here that most layouts that lateral spacing is going to equal the row spacing. In our case, we are just going to be considering what our lateral spacing is within each bed rather than considering those gaps between beds. That will come into play later on when we're considering the lateral layout along the manifold. So here we're going to say that we have 1 foot spacing between each of our 4 emitters within each bed. And then plant spacing, hopefully this would be provided by the landowner during your site visit, but if it's not, you can look up for your specific plant what plant spacing you're going to have. So we know that sunflowers should have minimum of 24 inches or 2 foot. And then here you're going to select your emitter spacing. So each manufacturer typically has some set emitter spacing for each tape that they sell, and we can just kind of pick one that would match our design, and we would as build to the exact tape that they're purchasing later on if they haven't already given you one that they are purchasing, so you can do that for the design. And I usually reference the Toro specifications for drip tapes, and you can find this information easily online for any product, drip tape product that you might be designing for. So here, as you can see in our outlet spacing for each of the emitters, we see, generally speaking, we go from 4 to 24 inch emitter spacing. There's one line that can give us a 36, but we're gonna try to stay between that 4 and 24 inch range. For this design, I'm just gonna go kind of in the middle and select 12 inch emitter spacing, and we'll see if that works. So, and again, you could have picked anything here and kind of go with it for your design if your landowner hasn't given you a specific product. So here it's going to tell you how many emitters you have per row. So since we have 1 foot row spacing and we have 1 foot emitter spacing and 2 foot plant spacing, we're going to end up with 2 emitters per row. If we were to change this emitter spacing to 2 feet to match that plant spacing, then we would only have 1 emitter per row cross section there. So going back to 12, and here you can pick your lateral layout type, and this is how your hose is going to be laid out within that high tunnel or just irrigation zone. But here we're going to go ahead and select single lateral, since we will have single lateral lines down each bed. But yeah, and you can see this diagram to the side will show you each of those layouts. And then here it's going to give us our percent wetted area, and based off of all this information that we put in, it's going to give us that our percent wetted area is 100%. So that basically means that 100% of our irrigated area is going to be wet. And since we're essentially watering the entire irrigated surface, the landowners aren't going to save a whole lot of water for this specific design, because the only areas that aren't going to be wetted are the walkways. So they'll be saving a little bit, but not a whole lot. So if you look on the flip end of things, if we had done this design and our percent wetted area was, say, 20% or 30%, then we're probably going to be negatively impacting the yields of the crops in this high tunnel. So you want to try to stay between 30 and 100% for this percent wetted area. For this problem, you might be able to talk with the landowner about whether or not they need 4 drip tapes per bed, or if just 1 or 2 would be adequate. In this case, if we go to 1 drip tape per bed, say we put that down the center of the bed, and then we have 2.5 feet to the outside of the bed, 2 feet walkway spacing, 2.5 feet to the other lateral, we would have 7-foot lateral spacing. And you can see here that it would drop our percent wetted area to 57%, which would be pretty good for this. But depending on where he's going to be putting his sunflowers within those beds, this 4-foot emitter spacing might not be great if he's going to be putting them on the outsides of the beds. So we'll go ahead and go back with what he wants for the design, and we'll go ahead and stick with 1 for our row spacing. And then down here, it's going to be discussing our maximum irrigation frequency. So this is the maximum amount of time that we can go between irrigating. So it will prompt you to select what amount of time you want your irrigation interval or frequency to be. In this case, we're going to stick to irrigating once per day, but you could pick anywhere from 1 to 13.5 days for your irrigation frequency. And then it automatically populates in our net application depth and our gross application depth based off of our efficiency and how many gallons per plant per day you will need. And then down here, it's going to be asking about our emitter drip tape, coefficient variation, exponent, and discharge coefficient. So if we go back to our Toro product specification, now we're going to have to select which emitter we're going to go with for our design. But we can see, at least for the Toro products over here, it gives us that every product has a coefficient of variation less than 3%. So for our design, we're going to go ahead and assume that this is 3%, since that's going to be our maximum coefficient of variation. And then in order for us to pick a emitter to go with for our design, I'm going to reference back to our PowerPoint and our 4.62 gallons per minute flow rate. So now we're going to take our diagram of our system, and knowing that we have 4 beds with 4 laterals, and each of these laterals are going to be about 46 foot long, and that's due to we have 50-foot high tunnel minus 2-foot walkways. So we'll assume 46 foot for our lateral length, and we'll multiply that by our 16 total laterals, and this will give us the total amount of drip tape that we will have for our system, which would be 736. So now we're going to take this 736 feet of drip tape and divide it from our flow rate that we found, so that 4.62, and then we'll multiply that value by 100 in order to find how many gallons per minute we need per 100 foot of drip tape. And in this case, when we do that math out, we find that we need at least 0.62 gallons per minute per 100 foot of drip tape. So we can look back at our Toro product specifications, and as you can see here, this Q100 gives us our gallons per minute per 100 foot of drip tape. So you can look at each of these 12-inch emitters, and you can try to look for where you see a 0.62 for that area. And here for our EAXXX 1256, we have 0.62 gallons per minute per 100 foot of drip tape at a 10 psi pressure. So we'll go ahead and select that for our design, but as I said before, maybe you go back and you change your emitter spacing and you just look through this whole table for anything that could match that 0.62 gallon per minute per 100 foot of drip tape that you need. So there are a lot of different choices that you could make here, but we are going to go ahead and stick with that EAX 1256 for our design. Okay, so now we'll go back over to our spreadsheet. And you could see on there that we didn't have values for both of these. So now what you're going to have to do is go into your EMK_X tab. And so this is going to help us calculate those KE and XE values based off of other known inputs from the product specifications. So here, if we go back to our Toro spreadsheet, I'm going to go ahead and split screen this. So if we go ahead and go back to our Toro spreadsheet, it's asking, okay, so at this pressure, so we know that we are going between 8 and 10, so we'll do 8 and 10. So at 8 psi, what is the flow rate in gallons per hour for that emitter? So here we can see our emitter flow rate, and you see gallons per hour here. So we're going to go to 8 psi and come down to our selected drip tape, and we see that it's 0.34 gallons per hour for that emitter. So you'll input 0.34 here, and then going over to the next column, that's going to be at 10 psi, so we're going to have 0.37 there. Once you input those values, it's going to tell you what your emitter exponent and discharge coefficient that you should input back on that emitter slide are. So we know here that we're going to go back and input 0.379 and 0.155. Now you could also scroll down here, and this spreadsheet has automatically populated numerous different manufacturers as well as manufacturer data for specific emitters for that manufacturer, and then it will tell you what the emitter exponent, discharge coefficient, and coefficient of variation is based off of that information. So we're going to go back to our emitter tab, and we're going to fill in that 0.379 and 0.155 that we had found for our emitter. And we're just double check, make sure that was right. Yep. Okay. So now we can move on to our lateral hydraulics tab. And so the first thing here, it's going to prompt you to input your design pressure. And as we had noted, based on the product specification sheet, we do need to be at 0.62 gallons per minute per 100 foot of drip tape. So we want to design our system for 10 psi. So we'll come in here and design our P inlet for 10 psi. Now you can change this and do your average pressure, your outlet pressure, or your inlet pressure. We're just going to stick with the inlet for this design. And then it's asking what our lateral length is. So we are designing on this tab for a single lateral. So we know that our single lateral is going to be that 46 foot long. And then here it's going to ask about our lateral slope, which we had found bringing in our survey data that was 1%. So if you are doing a really long lateral where you have a varied slope, you can actually come up here and click this varied button, and you'll be able to input stations with various elevations that would show that varied slope along the lateral. Here we're just saying we have an even 1% slope across the whole thing. Next, it's going to automatically input our emitter spacing based off of what we chose before. And then here it's going to ask about your lateral inside diameter. If we go back over to our Toro product specification, if you scroll over here, you can see the different diameters. For most of our projects, we're going to end up using these short reels since we're going to have a reel length typically less than that 3,000, 4,000 feet. So our producers are typically going to go with this 5/8 inch diameter reel because it comes in the short reel. So we'll put our 5/8 inch diameter in here. And then you can see over here that it gives you a Hayes and Williams friction factor populated based off of what pipe type you have, and then it pulls in what diameter you have for that pipe. So here we're going to say that we have lay flat drip tape. So for our 5/8 inch lay flat drip tape, our Hayes and Williams friction factor is going to be 130. And then you can see here that this is red. This means that we need to run this model. This 2.14 number was from a previous run of the model. It does not line up with our current values. So once you select to solve your lateral hydraulics, it'll take a couple of seconds, and then once it turns green, we know that this design flow is good to go. So we have 0.29 gallons per minute and the model is finished running. We see that our emitter information is automatically populated from that previous tab, and then this graph here is going to give you information for your lateral going down the distance of that single lateral. So it's going to give you that pressure at the input and at the output, your flow rate, which is going down to 0, which is a good thing, and then what your emitter flow rate is and your velocity is, which is also going to 0, which is a good thing. And then the next table is going to give us our pressure and flow rates at maximum, minimum, and average, and it'll tell you what stations those are at. And that's just coming from this table above. And then down here, we're going to be looking at if our flow variation and emission uniformity is good. So we want our flow variation to be less than 20% and our emission uniformity to be greater than 85%. So we are good to go, and these boxes are green. So we can go ahead and move on to our manifold tab. So starting with our manifold setup, it's going to ask us our number of lateral outlets. So for this problem, we know that we have 4 beds with 4 tapes each. So we're going to have 16 lateral outlets. So then you're going to look at your inlet position number. So this is where us asking the landowner where they would want to orient their hydrant is going to come into play. So you can see here, if your main line is coming from a center hydrant, you're going to need to determine which lateral that hydrant main line is coming into for the system. Since we have them coming in from the right, we're going to go ahead and say our inlet position is number 1. Then our slope across our manifold, this is something that you would find using your survey data, and we're going to say that when we pulled our survey data in, he had a 0% slope across where that manifold tube was going. But if you would have a longer manifold or really varied slopes, you could come in here and change the manifold slopes there, but we're going to keep it at 0 for our problem. And then here, again, if you have varied pipe inside diameter, you can go ahead and change that in this table, but because all of our pipe inside diameters are going to be the same for such a small manifold tube, we're going to go ahead and make an assumption for the design. I like to start out with a 1-inch manifold tube. You could start higher, you could start lower, and this number might end up changing based off of what we find when we solve for our hydraulics. So next, it's going to automatically pull in our row spacing from that lateral hydraulics tab. But as I mentioned before, on this manifold tube, this is where we're going to select that we have that varied row spacing. So you can see here that it highlights this table that was gray, and you're going to input information pertaining to your system. So when we think about our system in particular, we've got our 4 drip tapes that are 1 foot apart in each bed, and then there's a 2-foot walkway, but we have 1 foot also from the outsides of the beds. So we have 1 foot, 1 foot, 1 foot, and then we have 1, 3, 4 foot between the beds. So we're going to go ahead and go back to our spreadsheet. Alright, so our beginning number is going to be our first outlet. So number 1, and we're going to go to 4 because our 1 through 4 laterals are in that first bed and they have a 1 foot spacing. Next, from 4 to 5, so that space between our beds plus to the edge of the beds is going to be that 4 foot. And then from 5 to 8 is that next bed, and those are 1 foot spacing. Then 8 to 9, we have that 4 foot spacing again. And then 9 to 12, we have that 1 foot spacing. 12 to 13, we have that 4 foot. And 13 to 16, we have our 1 foot spacing. So this is how you would do a high tunnel setup where you have that walkway in between beds and you have that varied lateral spacing along the manifold. Alright, so then coming back over here, it's asking for our Hayes and Williams friction factor. So this is going to be dependent on your pipe type as well as your pipe diameter. So over here, it's going to automatically give you what that friction factor is based off of which pipe type you select, and it's going to pull this pipe inside diameter that you have here. So for our manifold, we're going to say that we have PVC and it's 1 inch diameter, so it's going to be 143 for that friction factor. And then next we're looking at our equivalent outlet length, and this is accounting for our losses from those connections or the barb loss for the system. So as we can see in this note, this generally is 0.1 to 0.5. So for our design, we're just going to put 0.1 here to account for some minor losses occurring along this line. Yep. And then we're going to come down here to our lateral tab or table. And here it is going to ask for our minimum emitter outlet pressure. So if you hover over this, you see here that it gives you that the typical value for this is 5 psi. We know that we don't want our emitter pressure to be at 0 psi because this is when you're going to end up having soil sucked back into the emitter. So typically we want to stay above 5 psi or at 5 psi. So for this design, we're just going to stay at 5. Right? And then moving forward, it pulls in your length and slope of your laterals and other information from that lateral tab, lateral tab before. And then our emitter values from our emitter tab. And then here is where our results will be. So we need to come back up here, and where it's red, we need to solve our manifold hydraulics based off of all of this information that we put in here. So you see that it's turned green. So now we have our manifold output results, and it's going to tell us what our block flow rate is, what our head losses for our block, what our emitter flow rates are, our emission uniformity for the block, and that flow variation. And if these were unacceptable values, then this would be red here. And you can see here that we have acceptable velocity along that manifold, so it is all good to go. Now, if you were to come down here and that manifold velocity were above 5 foot per second, you might need to change your pipe inside diameter, and you would just come back up here and you would change your pipe inside diameter as well as your friction factor. And then you would re-click this Solve Manifold Hydraulics to run the hydraulics again, and you would go down to check that your velocities were no longer in the red for your design. So we're going to switch this back to what our design is. Rerun it, and then we're going to move on to our Zone tab. So there's a lot of information in this tab. So our first table is giving us the option to adjust our flow rate or pressure or time, and then solve for the other two variables based off of your user input for that. And this takes into account our emitter orifice flow, our irrigated area, and our gross water that is applied. So you could use this to check if your system capacity is adequate, if the operation is efficient, and can work for the landowner's schedule. For instance, say here we are playing with the time, and the landowner doesn't want to operate for longer than half an hour. So you can throw in half an hour here and see that our minimum average flow rate is 0.42 and the average pressure would be 14. So we would either need to increase our time to irrigate or change some things about our current system. So you can play around with that and change those variables around to help with your design. So next we have our irrigation frequency table, and you can see here that it automatically populates in that irrigation frequency that we had selected on the previous tab. And then it's going to prompt you to input a percentage area of traffic lanes to subtract out from our irrigated area. In this case, for our high tunnel, this is saying to put in the percent area of walkways, the area that won't be irrigated within that high tunnel. So for our scenario, we know that we have a 1,500 square foot high tunnel with 4 beds that are 5 foot wide by 46 foot long. So we can take that 5 foot wide times 46 foot long and then multiply that by 4 to get that we have 920 square feet of irrigated area. We can subtract this from our total 1,500 square feet in order to get what our unirrigated or traffic area would be. So when we do that math, we find that we have 38.67% of our total area that is actually going to be unirrigated. So you can see here that some values in our other tables have changed. This is going to be, our area per emitter is going to decrease with this change. Our irrigated volume per emitter will also decrease here. Our time to irrigate is going to decrease. Our net application rate will increase here because we're able to apply more quickly with less irrigated area. And then obviously our irrigated area decreases to 0.2 or 0.02 for this system. So now the most important section of this worksheet is going to be our zone determination and system check here. So here it is taking that we have a system flow rate of 20 gallons per minute, and then it's saying how much flow we need per block based off of our manifold. It's telling us how many blocks we can have per zone and how many zones we could have. So if you look over here, it kind of explains more. So this gets into if we're going to have like multiple high tunnels coming off of submain, coming off of main line, you can kind of see how many you could do with the system set up as it currently is. So it's telling us that we could have a maximum of 4 blocks per zone. So we could have
62 zones and 4 blocks each. So we could have a very large system with a 20 gallon per minute water source here. So this check, if we didn't have enough flow coming from our system to meet our flow rate needed for our system, it would tell us that we can have 0 blocks, and that's where it would be a problem. We would need to reassess our entire design to make sure that we have enough flow coming from our water source to meet our needs. Alright, and so next tab we're going to go to is our flush tab. Once we're on this tab, scroll up to the top, you see our first table is talking about flushing the lateral. So it's going to input that lateral pressure from before of 10 psi, and then here it's prompting us to put a lateral flushing outlet pressure. And if you hover over this note here, it says if there's no back pressure on the system and our lateral is at free flow on the ground surface, then our outlet pressure will be 0 psi. However, if the outlet pressure is higher, then you will find what pressure needs to be overcome for the system to outlet that water. So you would use your increase in elevation to find your elevation pressure head by converting your feet to psi, and then if you have another factor that would be causing some back pressure like folded hose, then you would also add that pressure in for the total outlet pressure that is needed for the system. Here we're going to assume that our system, for example, is free flowing on the ground surface, so we're going to put 0 psi here. And then you click to solve your lateral flushing here, and you see that it populates in our flow rates and velocities for that lateral. And then you're going to come down here, and we're going to assume for our system we're not going to have a flushing manifold since we are free flowing the water flushing out onto the ground surface. We're going to assume that the landowner has end caps or clamps that are securing the end of the tapes. So for the sake of time, we're going to go ahead and move on to our filter section here. If you have a situation where you do need to solve for this flushing manifold, one of your engineers in your area can help you with that. So for our system, you're going to input your water concentrations from a water quality test or just some assumptions that you've made based on reported water quality from your landowner or what you know for the area. So as you can see here, whatever you put in for your particle concentrations here, it's going to recommend what kind of filter you have for your system. So for our system, we're going to say it's pretty good quality water, less than 5 parts per million for particles in there, and it's going to tell us that we need a pressurized screen or disc filter here. So then if you could play around with it and see, if you increase these numbers to greater than 50, you can see that it's calling for centrifugal sand separator, gravity flow screen filter, or pressurized screen or disc filter, etc. So we'll move on from that. So this next section is going to give us recommended mesh screen size based off of our emitter type. So typically, whatever product you're selecting will give you a recommended filtration size. So, for our Toro tape, it's recommending a 140 mesh filtration. But if you do not have that, then you can find this minimum flow path dimension for your emitter orifice or your emitter orifice diameter from our tables tab over here. So we're going to go into the tables tab and we're going to go to filter table 3. So up on the top, go to filter table 3. Oh, okay, it's the next table down. So table 4, you're going to pick what orifice type you have for your emission device or emitter, and then you'll come over and you'll find what that MFPD, that minimum flow path dimension was. So for us, our Toro drip tape has a tortuous emitter. If you look it up, it's tortuous due to a small labyrinth that is inside of that tape leading to that drip outlet. So we'll go in here and we'll go ahead and take that 0.039 value back to our filter tab. You would input that here, and it's giving that recommended screen mesh size as 150. Over here you can do your user selected screen size. Since we saw on that Toro product specification sheet that we had a 140 mesh recommended size, we're going to go ahead and do that for the design, and it's going to show red here because it's less than what our recommended screen size was. But the 150 mesh screen would be better for removing those finer particles that would cause your drip tape to clog easier than the 140 mesh, but because of the way the Toro drip tape is designed, they only require a 140 mesh, so that's what we're going to go with for our design. So then for our project, your flow rate per unit can actually be found from the manufacturer for the screen selected. So you're just going to go over to Google and see what the flow rate for a 140 mesh screen size would be. And it looks like for a 1-inch 140 mesh screen, it can handle up to 50 gallons per minute. So we're just going to select a 25 and kind of go in the middle there. Alright, and then it's saying here how many units are required for our system. So if that unit that you selected could only handle a flow rate of, say, 5 gallons per minute, it's going to tell us that we need 4 of those for our system because we have 20 gallons per minute going through there, and if it can only handle 5 gallons per minute, we would need 4 of those units. So here we can handle 25, so we only need 1. Now looking at the sand and media filter design information, since we don't require a media filter for our design based off the recommended filters, we are not going to be using these tables for the sake of time today. But if you need them in your future designs, there are notes associated with each of these variables that you'll be inputting and getting out of it that would help you with the design process, or as always, contact your area engineers for further assistance. So now we're going to go to our mainline tab. So this tab is going to go over our main line. So that's going to be our main water line that is bringing water from our water source to our hydrant or manifold tube. So here in this table, we're going to say that that flow rate in the pipe is what our flow rate coming from our well is, which we said was 20 gallons per minute. And then it's going to ask for your pipe inside diameter, and we can start with the same diameter as our manifold tube and adjust that as needed. But to get our exact pipe inside diameter, you can see that there's this table over here to the right. So in this case, we're going to be using our high density polyethylene pipe, and we're going to go with ASTM 2239 for this project. But obviously you can select whatever you are choosing to design for. So our ASTM 2239 is a standard inside dimension ratio pipe. So we're going to change this to SIDR. And now if you go with something like the ASTMD 2737, it is a SDR pipe and you would go with that. So we're going to start with a 1-inch nominal pipe, and our wall thickness here is going to be from our drop down menu here. So you can see a few different options, but when you click on each option, it's going to tell us what the pressure class of the pipe with that wall thickness is. So for most of our projects, at least here in Area 5, we are looking to get at least 200 psi for our pipes. So we'll go with that 7 wall thickness option there, and have our 200 psi for pressure class. So with that, you get your pipe inside diameter of 1.049. So you would come over here and put that in. And then our pipe length is going to come from our survey of the area, from the water source to where that water line is going into the hydrant or manifold is what our pipe length is going to be. We're going to say in this example problem that we measured that to be 150 feet based off of our survey. Now it is asking about our friction coefficient, which can be found in the tables section if you do not know this already. So coming over here to our table, you're going to scroll up to find where you have your pipe material and the given Hayes and Williams friction factor. So here we're looking for PE pipe that is 1.049 inside diameter. So you see here 1.049 would be between these two, so we're going to have a 145 Hayes and Williams friction factor for this. So we'll come back over here to our mainline tab, put that in, and then here you're going to indicate any elevation change from that water source to your system. So if you're going downhill, you're going to use a negative sign, and if you're going uphill, you're going to keep it as a positive integer. So in this case, we're using our survey data, and maybe we find that from the well to the hydrant, we have an increase of 10 foot in elevation. So this is going to populate what our pressure loss and velocity in that pipe is. And then down in this table below, it's going to bring in what your minimum pressure at your water source is going to be based off of your losses. So here we see that it's prompting us to also put in these minor losses. So what you're going to do is scroll down here, and you're going to put in each of the appurtenance types that you have for your system and how many they are, and then it will calculate out your minor losses based off of those appurtenances, and then you can type that number in up here. So for our system, we are going to say that we have a one standard 90-degree bend. We're going to say that we have a T. We're going to say that we have a swing type check valve. And we'll say that we have a globe valve. Now you would do whatever actual appurtenances you have, not just making assumptions here like I am for this design. And then down here you can also put if you have expansion and contraction appurtenances to account for in your minor losses. So based off of this, we have 4 psi for our minor losses. So we're going to come back up here and you'll put 4. And then you see that our minimum pressure at our source is going to be 40.11 based off of our mainline pressure loss due to head loss, minor losses, filter losses, all within our system. So you can see here, you know, our pressure at our source is 60 psi. But if we were to say have an instance where our minimum pressure at our source is greater than what our pressure at our source is, this block will turn red to let you know that this system is not going to work with the pressure at the source that is needed. Now that we have all of our information loaded into our spreadsheet, you can come over here to our summary tab and you can see that it populates in summaries from each of those tabs that we populated, and it gives us, you know, our block emission uniformity and flow variation, which is green, and it's all good to go. So then we would print this out to put into our design folder.
Okay, so the design example is over. You will print all of those out and put those in your design folder at the end of the project, along with those reports from your IWR spreadsheet. I don't see that there were any questions in the chat, but Kelly did note that on my lateral hydraulics tab, I did say that our pipe was the lay flat pipe. And typically our lateral pipes are going to be PE for that, and we'll see the lay flat in our manifold. So that would just change what our Hayes and Williams friction factor was for that calculation there. Are there any other questions? Thank you, Kelly. All right, well, everyone, enjoy lunch. Thank you for joining us. Thank you, Logan, for all of the work that you put into this, and thank you, Kelly, for all of your help with going through the spreadsheet.
Yeah, thank you, everyone. If you have any questions, reach out to either your NRCS or your ODA engineer or Alyssa and I.